Yet. Okay, got it.
Yep. All right. Good morning, everybody. We're recording now, so if any issues, let us know. This video will be posted to the Open Oximetry website. Each of the talks will be there, and the chat is being recorded, and meeting minutes are taking place in the same Google document that is posted on the Open Oximetry community page, so you can follow along and add to those notes as we were yesterday. Each of the sessions, same as yesterday, we'll have moderators and speakers. We're going to try and go through all the speakers and save Q&A and discussion for the end of each session. And then at the end of the day, similar to yesterday, we'll have some open forum time and a wrap-up session where we'll discuss kind of a summary of the last 2 days.
And briefly, if I might mention, it would help to have concrete ideas, i.e. written down sentences as to what you are trying or what you want to accomplish if you have a particular requirement or statement. Because at the end of the day, if it's not written down, it's not actionable.
So it's not only the problem, but how you think it might be corrected as well, or the rationale for it.
Thanks, Sandy. Thanks, Bob. Yeah, and just to follow up on that, we discussed yesterday, at the end of the day, we will go around for those who are online and want to contribute either through the chat or by raising your hand. But everybody in the room will go around and we'll try and provide kind of our at least our list of our top 3 very succinctly changes that we're proposing. Couple reminders about the meeting structure. Everybody online, please keep yourself on mute. If you want to speak, we encourage that. Please use the chat function. Or please raise your hand. For those of you who are in this room, please join the Zoom, but leave computer audio so we don't run the risk of any feedback. And here's how to do that. If you have any issues with that, please ask either Fifi or myself, and we'll come help you out with that. This is how to raise hands. As a quick reminder to those who aren't familiar with Zoom, the reactions button, raise hand. Don't forget to lower it if you've already made your point. Special thanks again to the funders who are supporting this meeting, to our co-host, to Fifi Negusi, who kindly celebrated her birthday with us here yesterday. So, yeah.
What a waste.
To the Chessa team and to the moderators and speakers again for taking the time today. So without further ado, we're going to jump into our first session in just a moment. I was going to mention, most people are online in this room, but for those who are in San Francisco, we're going to start off by just going around the table very quickly. Please state your name, your institutional affiliation, your title, and if it's not obvious in that, why you're here, please say why you're here. So maybe we could start down there.
Hello, everybody. My name is Daniel Franklin. I'm a faculty member at the University of Toronto. Our group makes wearable devices and implants, but we focus mostly on biophotonics. So looking at possible solutions overall discussing today.
Thanks for joining.
My name is Steve Groen. I'm the global product manager for Philips Pulse Oximetry. I own algorithm cables and sensors. I'm a nurse by background. I'm from Philips.
Thanks for joining.
My name is Rolf Neumann. I'm working for Philips. I'm R&D leader for the physiological measurements, and I've been working in the Pulse Oximetry community for more than 20 years, and now handing over to Yvonne.
Yeah, so I'm Yvonne Motz. I'm also working for Philips. I'm a hardware engineer as a background, been doing hardware the last 10 years or something, and now I'm transitioning with taking responsibilities.
Welcome.
Hi, my name is Mike Jaffe. I've been involved with Pulse Oximetry for the late 90s, and I've been told Sandy's fault, as I am. And you can actually look the story later. And I actually work for both the MDP&P group at Mass General as well as Philips, and I'm here in the meeting on behalf of Philips.
Thanks very much.
Paul Batchelder, Chief Clinical Officer of Clinimark, which has been recently acquired by Element, and been working in this space with the Standards Committee since the early 90s.
So I'm Phil Bickler. I'm a professor of anesthesiology here at UCSF, and I am the director of the UCSF Hypoxia Lab.
Bob Kapotic, you've heard a lot about the ISO side, and so Sandy and I have done that for a while. And I work for Edwards Life Sciences, and they have no oximeter for pulsation measurements. So I'm here, I guess, volunteer then.
Hi everyone, I am Fifi Negusi. I work here at UCSF with Chessa. I am the program manager.
You guys have heard from me. And over to Kelvin. Sure. Good morning, everyone. Kelvin Moore, second-year medical student at UCSF, and I'm also part of the Open Oximetry equity team and a research assistant for the Equiox team.
Hi, everyone. My name is Jenna Lester. I'm an assistant professor here in the Department of Dermatology, and I'm here to moderate the session today and discussion of skin tone.
Hey everyone, I'm Leo Shmulovich. I'm a pediatric dermatologist and a professor of biomedical engineering at WashU. I do research in skin imaging, and I'm really excited to talk to you today.
Hi, I'm Amy Moran-Thomas. I'm an MIT professor in medical anthropology, and part of the anthro engineering approach that we're trying at MIT is to kind of bring user feedback into dialogue with engineers who might not hear those perspectives. So I'll be presenting together with Adia Benton, a professor at Northwestern, a very well-known medical anthropologist, and we're representing the Society for Medical Anthropology.
Thank you. Mike.
I'm Mike Bernstein. I'm a consultant in Pulse Oximeter development and testing, and I've worked for a lot of major pulse oximetry companies in trying to develop or test their equipment.
Jake Dove. I work for Medtronic on the R&D side, closely in pulse oximetry.
I'm David Milks with Medtronic in patient monitoring oximeters and principal statistician.
Okay.
I'm Wim Verkruijsen. I work at Philips Research in Eindhoven, the Netherlands. I have a background in tissue optics in the field of laser dermatology. In the past 10 years, I've been mostly working on camera-based pulse oximetry.
Jeff.
Yeah, Jim Stafford. I'm from Global Health Labs, a development engineer, primarily interested in like adapting or using common sensors and devices that we have PHC and community health centers and lower income countries to kind of cash shift some of the stuff down to lower levels of health care.
Thanks, Jim. Carolyn.
I'm Carolyn Hendrickson. I'm a pulmonary critical care doctor at the County Hospital and associate professor at UCSF. I lead the Equiox study, which is the real world sort of ICU study, prospectively enrolling patients in the ICU to test pulse oximeter accuracy.
Everyone, it's a pleasure to be here. I'm Vikrant Sharma from Massimo Engineering. My background is PhD biomedical optics, about 10+ years of experience in tissue optics and pulse oximetry, co-oximetry. So pleasure to be part of it.
Thanks very much, John.
And I'm John Feiner, Professor Emeritus now at UCSF, part of the UCSF team. Been performing pulse oximeter studies here for over 30 years. Part of my focus has been on the engineering and data analysis side, as well as putting in the A lines and being a volunteer subject until I was age 50 and had to age out.
Thanks, John. Bill.
Bill Wilson, I'm the Chief Medical Officer at Massimo. I have a long interest and experience in monitoring, starting at UC San Diego, where I was on faculty in the Department of Anesthesiology, as well as at UCSF, where I was a critical care fellow and a surgery resident, and then at UC Irvine, where I was Chief Medical Officer for 5 years and in charge of all the ICUs for about 5 years there. Now at Massimo. Thank you.
I'm Sarah Teeley. I'm a mechanical engineer with Clinimark, and I'm slowly starting to transition and take over some of Paul's roles at Clinimark.
Thanks, sir. Greg.
Hi, everyone. I'm Grant Aaron. I'm the VP of Global Health at Massimo, which is, a core, probably the most central theme in global health is skin pigmentation. So have engaged with Mike and just excited to be here to see people that I've read papers about and to learn more and engage with the most engaged people in pulse oximetry in the world. So thanks for having us.
Thanks very much. We're not going to go around and do introductions for everybody online. Apologies. I do want to highlight one quick thing before we jump into our first session, which is the diversity of the conversation. Part of the Open Oximetry project is really focused on trying to broaden the voices that are part of this discussion on trying to address this problem. I think if we look around this room, it's not the most diverse. I just want to highlight that. And some of that is self-selecting, and it is a problem that we can fix. And I think in doing so, we will be able to find solutions that may have eluded us to this day. And so we are working hard to try and invite more people to this discussion. This is one of many. And I think a lot of that, for logistical reasons, are going to not necessarily happen face-to-face, but we hope as we have more meetings that we can see more disciplines, more geographies, diversity in every way that you can imagine at the table, and that we will have a lot to learn from that cross-pollination. But I do want to highlight that this is a work in progress. I don't think we're there yet, clearly. And that's something that I think we all need to think about, because issues that we're discussing today impact the majority of the world, which is not represented at this table. And so I just feel that that needs to be mentioned explicitly. So without further ado, this morning, we're going to be talking about the issue of skin pigmentation, skin color quantification as relates to the standard, and how we could do a better job, and how that may contribute to improved patient safety, improved health equity. And we're very lucky to be joined by many speakers this morning, and to have this session moderated by Dr. Lester and by Kelvin Moore. So thanks very much for joining. I'll hand it over to you guys.
What I didn't mention when we were going around the table, I am the director of the Skin of Color program here at UCSF. Skin of Color is a discipline in dermatology focused on the skin concerns of patients with dark skin tone. And an issue we've been grappling with in dermatology in general is inclusion of images of these people in textbooks and teaching, especially in teaching. And there have been a number of reviews over the past several years looking at the fact that there's dramatic underrepresentation of brown skin tones when we look at educational materials. So pigmentation is something that I deal with in a clinical setting, and we talk about skin tone a lot in that setting. So I'm really excited to first introduce Dr. Ellis Monk, who I believe you heard from yesterday. He's associate professor of sociology at Harvard, and he developed the Monk scale, which is something I'm excited to learn more about today, especially as we grapple with these issues and how to quantify skin tone, so that we're making sure we're delivering best products and best care possible. So with no further ado, Dr. Monk.
Mike, can I make a quick comment before Dr. Monk dives in? Because we're trying to also impact and improve the standard, I will be attempting to paste in the clauses that I think are relevant. And if you watch the chat box, if you want, or if I miss something, by all means say, hey, Sandy, what's the clause for the following?
Thanks, Sandy.
Okay, so yeah, my name is Ellis Monk. I'm at Harvard University as a sociologist. So I'll go ahead and jump right in. I know we've got a long day, so I'll try to keep this snappy. So what I'll be talking about in this presentation is the value of subjective, as they're called, visual scales. So as I think we all know now pretty clearly, one of the key issues that people have highlighted is the relatively homogeneous pool of study participants in trying to calibrate and try to test pulse oximeters. And right now, the standard, as I've read it and understand it, is that at least 2 volunteers of a study group, or 15%, whichever is higher, should be darkly pigmented. But of course, this raises the question of, well, what do we mean by darkly pigmented, especially when we're thinking about these visual scales that people use? And this has huge implications across a number of different types of devices, from NIRS, bilirubin detectors, infrared thermometers, self-driving cars. This is a huge issue in machine learning and artificial intelligence, which I'll go into more detail about as well today, and facial recognition technology as well. And this group from Homeland Security pointed this out, talking about the Fitzpatrick scale and facial recognition technology specifically, and I'll go into more details about that as well. So one scale that's used as part of this kind of, norming, calibrating research is the von Luschen scale. And I won't talk too much more about the von Luschen scale today, because I know the anthropologists are going to talk about this in more length and more detail, but I just want to point out a couple of things just in terms of practicality. So in the past, when this was developed, and this is a very old scale that finds its roots in colonialism and actually racial classification, not skin tone classification. The reality is a lot of people kind of print this Von out, and there are some issues around finding the right version of the scale, and and dialoguing with some of the people who have been doing this work like Mike, and you can feel free to speak to this if he wants to or not, but my understanding is that sometimes the prints are not as standard as they should be, and maybe a couple of the different colors on here are actually exactly the same even. So there's a lot of issues around the standardization of this Von, and it's 36 points, which practically speaking raises issues around how much consistency and reliability there is with human raters subjectively using the scale. But the main scale that people tend to use the most is this Fitzpatrick scale, which I think we all know pretty well. One thing I'll highlight really quickly here is that there seem to be a lot of different types of Fitzpatrick scales floating around on the internet as well. So there's some questions there around, are people using the right one or not? And I'll talk a little bit more about why I think there's some issues there. But in terms of etymology, where it came from, right, the origins of the scale go back to the 1970s. Dr. Thomas Fitzpatrick at Harvard Medical School, also at Harvard. And one thing to point out about the Fitzpatrick scale is that it wasn't actually designed, it wasn't intended to categorize skin tone. Instead, it was really about dosing for phototherapy, particularly in white patients, in UV therapy for things like psoriasis. And there's some evidence from the dermatological community that it's inconsistent even when used as intended. And despite not being actually designed for the purpose of skin tone classification, it's been taken up as this kind of gold standard of skin tone classification, not only by dermatologists, but in the machine learning artificial intelligence community, and of course in pulse oximetry. One thing to point out about the scale is that originally it was only 4 tones. And about a decade after that, 2 more tones were added to try to add a little bit more diversity to the scale. And as one kind of overriding theme here is that a lot of the criticisms around the Fitzpatrick scale that we see among dermatologists and people in pulse oximetry really mirror the criticism around the scale in machine learning and artificial intelligence, where data set construction, data annotation, and the algorithms that flow from all of this and things like facial recognition software, self-driving cars, automatic face detection, image classification, all of these things, they're all vulnerable to biases when the standard of measurement for skin tone is not as inclusive as it could or as it should be. Specifically, some studies find that the Fitzpatrick scale excludes the majority of African Americans and overestimates the number of African Americans that have type 4 skin. Specifically, there's a quote there that says the Fitzpatrick scale provides a restricted range of options for people with darker skin tones that do not capture the variations in their color. And again, they point out that even when used as intended, there are some issues there, especially for ethno-racial minorities. Now, one other wrinkle I want to point out, and this is based on my research developing the Monk skin tone scale in particular, is that ironically, I think one of the issues with the Fitzpatrick scale is that it's simultaneously too dark for many white people and not dark enough for many ethno-racial minorities. I mean, we could do a quick test in the room, people could kind of look at their hands or, all of that, but type 1 on the Fitzpatrick scale, and I think people are going to talk about this a little bit more, but these colors are really about what happens when you tan, right? When you're exposed to UV. So if you look at even type 1, which says light pale white skin, I would argue that, the face validity there is a little bit lacking. I would argue that there's a lot of white people or non-Black people who have much lighter skin than type 1 on Fitzpatrick. And then again, if you go out on the darker end of the scale, arguably it doesn't get dark enough. There aren't enough, variations in terms of the types of darker colors that it has. So I don't think it's the case that it only is having issues for people who are not white. I would argue that even the light end of the scale isn't light enough, and the Fitzpatrick kind of lives in this intermediate zone, which again, it's its roots in tanning and what happens to skin after tanning, right? And the group out of the Homeland Security that was talking about facial recognition, they pointed out a lot of these similar issues. They came to very similar conclusions, saying that the FST was originally this questionnaire about, treating psoriasis. It's not skin color. It wasn't supposed to be skin color, and there's mounting evidence from the medical community that it's less reliable for an assessment even when used as intended, particularly for ethno-racial minorities. And as they point out here, I have on the slide, the computer vision community, similar to dermatology, pulse oximetry, et cetera, has kind of adopted these 6-point scales as Fitzpatrick skin type. So there's been this kind of conflation where any 6-point classification has been conflated with like Fitzpatrick specifically, and that's not necessarily the case. And I think the proliferation of different types of Fitzpatrick scales all around, the internet kind of builds into this. And they came to this kind of similar endpoint, which is if we're reaching a consensus standard measure, is this the right one? Are we measuring it the right way? So there also are some alternatives from the social sciences. The first one, the real main one that I see a lot in the social sciences and someone who does health research is the Massey-Martin scale, which was designed way back in 2003, actually by my former colleague at Princeton. We overlapped at Princeton. He was a great mentor to me, Doug Massey, and he used this to study colorism and skin tone stratification among new immigrants to the United States. And this measure has been used to measure skin tone in the general social survey, which is, again, this really big project that's been going on for decades to give us information about the social world, politics, et cetera. Now, one thing to point out about the Massey-Martin scale is that technically it's an 11-point scale because they wanted to also point out that there are people who lack melanin, who might be albino, right? So they actually say that this is 0 to 10. 0 not being represented on the scales explicitly. But one thing that's really nice about this particular scale is that they tried to kind of do shading, they use hands, they try to make it something that, feels a little bit more like human skin. Now, of course, this is almost 20 years old now, so they did a lot with the technology they had back then. But some of the criticisms in terms of this particular scale is that, it has poor differentiation on the darker end of the scale. Lots of the time people remark that they have trouble differentiating anything beyond a 7. And I think people can kind of see that it starts to get a kind of blue towards the end of the scale. And there's some research that suggests that there's reportedly low levels of agreement and consistency when people use a scale. I think some of this criticism is a little unfair because if you look at the original instructions, one of the things it says is that people should memorize the scale. And this is because of the way that the scale was being used in field research. They didn't want the respondents to see the skin tone scale that the person was using in the field, interviewing people as part of a large survey, right? And I think that's why some of the results on consistency have been quite so low over time. You can see here from one paper that came out in 2016, they're reporting like ICC of like 0.451, 0.279, like very, very low, far below like 0.8, which is what I think a lot of people would want to see for a visual subjective scale. That being said, there are some more recent papers that have come out, which I think report much higher levels of agreement and consistency, even with the Massey-Martin scale, but they've used smaller samples. And that brings me to the scale that I designed, which, I really view as an evolution of what, Doug Massey was trying to do. Similar to the Massey-Martin scale, the Monk scale was designed explicitly to measure skin tone in diverse populations. And one thing about a subjective visual scale is that, they're intended to be easy to use. They're intended to be reliable and cost effective. And when we think about the global health implications here, I think it's important to keep that in mind, the value of these visual scales. And again, with a scale, you don't want to give people so many choices that there's a lack of consistency, agreement going on with the scale, but you want to have enough options on that scale. And you want to have the choices that are made on the scale. What tones and undertones to represent on a scale that are going to give people the best approximate choices when they're doing skin tone classification. And that's really the main way that I argue that this scale improves on prior scales, which is that it's providing a wider range of carefully selected skin tones to better represent the dynamic range of differences that we see in the United States and beyond. And the color selection was based on my extensive fieldwork in the US and Brazil. Specifically, I also use computer software that social psychologists use to create facial stimuli for social psychological experiments, which had skin reflectance scores. And I consulted various maps of the distribution of UV exposure and human skin tone around the world. And I validated the scale in multiple ways. The first way was through qualitative cognitive interviewing with NSHAP, and I'll go into that in a second. And the second way was through nationally representative surveys. So this is a picture of the scale with some instructions. And I'm happy to see that a lot of different research teams that are tied to the Equiox and Open Ox projects are beginning to include the Monk scale in their protocols. So I'm really glad to see that. And the first kind of wave of validation, and this is prior to the scale's adoption by Google, first and foremost, most of my research is on health disparities in the United States. So I'm part of the investigative team. I'm an official investigator on NSHAP, which is the National Social Life, Health and Aging Project. It's a gold standard health, aging, and epidemiologically focused survey. It's received over $50 million thus far in funding from the NIH and NIA. And I help lead some cognitive interviewing around the scale for our field researchers and some participants to see how they felt the scale was able to be used in field research and how well they felt like it represented the different skin tones. We oversampled people who were Black and brown, and the scale was adopted. It ended up being adopted by NSHAP beginning in 2021 for their fourth wave of data collection. And then after that, it was adopted by Google. Google has adopted it across a wide range of their different products. There's some blogs online where they explain the ways that they're using the scale right now. And the main idea, and this is what I'm trying to highlight here, a lot of what we're discussing in pulse oximetry, there's huge overlap in machine learning and artificial intelligence. The main idea here is that in order to have products, say like filters on different cameras that people are using, things like in image search, computer vision in general, you need these visual scales because of data set construction, data annotation, etc. Okay, so they have adopted this scale as a replacement, as an alternative to the Fitzpatrick scale to improve all of their products in terms of skin tone representation. And this is a paper that is under review with myself and people who are working at Google. And this is one of the first validation studies that we worked on. And what we did in this study was we used a nationally representative sample of the United States to compare perceptions of inclusivity and representativeness of the Fitzpatrick scale, the Monk skin tone scale, and a 40-point cosmetic industry scale. And this is the main finding, which is that not only is the Monk skin tone scale, from the vantage point of a nationally representative pool of survey respondents, perceived to be significantly more inclusive representative of their skin tone than the Fitzpatrick scale, but there was no statistically significant difference in perceived inclusivity between this 40-point scale and the 10-point Monk skin tone scale. Similarly, if we look along the skin tone continuum here, we see that we don't really lose any terms of perceived representativeness among lighter skin or medium skin people, but there is absolutely a huge uptick in terms of the perceived inclusivity of both this 40-point scale from industry and the Monk skin tone scale, which is only 10 points. Again, this kind of highlights then that the basic idea in the literature has been that the Fitzpatrick scale doesn't do a great job of representing darker skin tones. In our validation work here, we confirm that, and we find that both the 40-point scale, which is rather large, and the 10-point Monk skin tone scale does a much better job, particularly for darker skinned people, representing their skin tones. And these kind of results led to the adoption of the Monk skin tone scale by Facebook Meta. They announced this just last week, actually, kind of good timing, in their Casual Conversations V2 data set. And what this data set is, as you can kind of see there on the slide, is that, as they explain, developing robust, fair AI systems requires data sets with a comprehensive set of labels to help ensure the validity and legitimacy of various measurements. So they have adopted the Monk skin tone scale as well, in addition to the Fitzpatrick scale, in order to improve the robustness and the diversity and the inclusivity of a lot of different AI and machine learning applications. And this data set is now publicly available online. Here's a little blurb from their write-up about the V2 version of this. And V1, they only use the Fitzpatrick scale, and V2, they added the Monk skin tone scale. And there's a technical report paper where they explain this new data set. And one thing I want to point out here is that if we look at the comparisons between the distributions in the Fitzpatrick scale and the Monk scale that Meta, Facebook have provided here, if you look at 4 and 5 on Fitzpatrick, one thing to point out is that a lot of the analyses that people are doing with the Fitzpatrick scale, they tend to combine 4 and 5 together. And then they will dichotomize, they'll say that's dark, and then they'll compare it to 1 through 4. Well, Fitzpatrick 4 is dominated by Monk scale 5, or the letter E, the middle of the distribution, as you can see. And this data set was oversampling people from India, Brazil, the Philippines, Indonesia. So we should expect a lot of people based on the distribution of skin tone around the world. There should be a lot of people in those kind of more intermediate skin tone categories, absolutely. But one thing to point out here is that even Fitzpatrick 5 is dominated by Monk skin tone scale 5 and 6, which is to highlight one of the issues here with the Fitzpatrick. In using the Fitzpatrick and the way that people dichotomize and they bin these categories in their analyses, you may actually end up leaving a lot of darker skinned people out of your analyses and out of these testing procedures to calibrate and to validate these pulse oximeters. And this is the same thing that's been going on in facial recognition software, self-driving cars, you name it, it's the same issue, which is that you're actually leaving off some of the darker skinned individuals by having the Fitzpatrick scale as your standard of measurement. And the other thing to point out here is that a lot of African Americans end up getting put into Fitzpatrick 4, which, as you can see here, is 4 and 5 and 6. It's really this middle range of the scale. And yesterday I took a screenshot, please forgive me, from one of the presentations, but you can kind of see a very similar dynamic here, where if you look at the Fitzpatrick scale, you see people maybe about 4%, 4.5% are in 4 and 5. But if you were to look with the Monk skin tone scale, you basically see no representation beyond the letter G, which, 7, 8, 9, 10 on the scale, right? So what this means then is that there's this truncation effect going on where darker skinned people may not be included in the study, but they may end up in Fitzpatrick 4 and 5 or 5 and 6 and give you this impression that you do have darker skinned people in your study. So by way of conclusion, I just want to say that a lot of the visual scales that are out there, they're cost effective. A lot of the studies show that even things like the Massey-Martin scale are potentially reliable ways of measuring skin tone in diverse populations. And most scales correlate strongly, at least with L star, which is just lightness to darkness, despite the color selection or how unrealistic some scales may look. And again, I want to highlight, like, most scales have relatively decent levels of consistency and reliability, but current practice relies heavily on the Fitzpatrick scale and/or von Luschen, which has come under criticism for not adequately capturing a diverse enough range of skin tones, especially for ethno-racial minorities, people who aren't white. And notably, the Fitzpatrick was never designed for skin tone classification in the first place, and neither was the von Luschen, which really finds its roots in colonialism and racial classification. So in terms of the regulations, currently we target 2 people or 15% being darkly pigmented, but this may potentially leave out darkly pigmented participants. One, if scales are not diverse enough, especially at the darker end of the scale, and if studies lump together multiple categories from the scale in a way that allow lighter skin participants or those who are in medium categories to be coded as darkly pigmented, okay? So one of my kind of explicit recommendations here is that the 2 or 15% regulation should probably be revisited. And I think Medtronic, if I remember correctly, was already beginning to do some oversampling of people who are darkly pigmented. Again, what do we mean by darkly pigmented? So in terms of the Monk skin tone scale, I just want to point out it was explicitly designed to measure skin tone in diverse population. It's already been adopted in large-scale ethno-racial health disparity research. It's been adopted in machine learning and artificial intelligence by both Google and Meta Facebook. And academic research that's ongoing, but some of our internal testing shows that the skin tone scale is not only perceived to be more inclusive than the Fitzpatrick, but it has excellent rater agreement as well. Some of our reports say anywhere from 0.91, 0.96 ICC, and this is globally using a pool of raters from all over the world. Thank you very much.
Thank you.
So we're going to continue on. Our next presentation is from Dr. Leo Shmulevich, who's an assistant professor of medicine, radiology, physics, and biomedical engineering in the Division of Dermatology at WashU in St. Louis. His research interests include developing low-cost optical imaging devices that are globally accessible and developing methods to quantify skin mechanical and optical properties. So without further ado, thank you so much.
Okay, thank you so much. Looks like the screen sharing is correct. So I am really excited to be here. Thank you for the opportunity to speak today. I would like to disclose that I'm the co-founder of a company that's developing wearable laser speckle imaging devices, and that may relate to discussions of peripheral perfusion. But as we start, I'll point out that in dermatology, we know that skin pigmentation has impacts on how rashes can appear by eye. For example, both of these patients have clinically significant poison ivy, but in the patient with pigmented skin, the more subtle appearance by eye could result in misdiagnosis or an underdiagnosis of the severity of disease. And this has direct parallels to what we've been talking about with pulse oximetry, because in both cases, those people who are already affected by racial disparities in healthcare are subject to potential misdiagnosis or underestimation of disease severity. The potential root cause of this issue also has parallels. They include questions of how strong the signal is to background, as well as issues tied to structural racism that Dr. Lester is an expert in and has written extensively about, and I urge you to look at her work for learning more about that. As I've been thinking about the connection between pulse oximetry and pigmentation, I tend to think about clinical cases that may help shed some light into this question. And so in particular, patients who have differences in melanin distribution, particularly in pulse oximetry sites. So for example, the patient on the left has vitiligo. They would identify most likely as black, and there's no fingertip pigment. Are they still at risk for the occult hypoxemia that Dr. Schoding has found? What if, let's say, one side was depigmented and the other was pigmented? Let's say a placebo-controlled trial where it's a split body trial, we repigment one side and do placebo on the other. Could that patient serve as a control of their own self, where you would put a pulse oximeter on opposite sides and be able to deduce what is the impact of pigmentation? On the other side, you can imagine a white patient who has a streak of melanin in their nail due to something called longitudinal melanonychia. It's not melanoma, it's just a mole that happens to live in their nail matrix. Would this patient now be at risk for occult hypoxemia? These cases potentially decouple these racial health disparities that we're talking about from this underlying pigmentation in skin. And I think if we could find a way to enroll subjects like this in clinical validation studies, it could be potentially very powerful. With these considerations in mind, let's discuss skin optical properties and skin color, which are not exactly the same thing. So as a quick review, melanocytes are these cells that have these tentacles. They live at the basal layer of the epidermis. They package melanin in these little containers called melanosomes, and then pass those melanosomes to keratinocytes. And those keratinocytes wear the melanosomes like a hat directed towards the sun to protect themselves from sun damage. There is no real difference that's known in terms of the number of melanocytes between people with lightly pigmented skin and darkly pigmented skin. The number is the same. What's different is that the size of the melanosomes is different. The amount of melanin in the melanosomes is different, and the number of melanosomes is different. And those differences likely contribute to some of the optical properties differences that have been measured in actual human skin. So this study from Sang et al. Measured dorsal form absorption and reduced scattering coefficients in subject with Fitzpatrick type ranging from 1 to 6, and found higher absorption and higher scattering coefficients in patients with pigmented skin, particularly in the red wavelengths. So making the connection between skin optical properties and the observed skin color that we see, that is not so trivial, right? Skin is a complex multi-layer material that has wavelength-dependent absorption, wavelength-dependent scattering. What we observe by eye is the sum total of all of those interactions. So this complexity, one way to appreciate this complexity is to look at clinical lesions like I'm showing you here. 4 different lesions, all made of melanin, right? So when the melanin's close to the surface, it can look brownish red, it can look brown, it can look black. When the melanin is deeper, suddenly it looks blue. So context is absolutely essential for understanding what we see and how that connects to the optical properties that something is made of. Ellis talked a lot about this, so I'm not going to go into detail, but as a dermatologist, I have to say something about the Fitzpatrick scale. It's one of several scales that are proposed to delineate differences in skin composition. It was designed in the 70s specifically to predict what dose of UVA should I give for someone who's undergoing therapy for psoriasis. And it was specifically for a trial of PUVA in white people. That's what it was. It is a survey-based questionnaire, not a visual scale. And the reason for that is because when you, as Fitzpatrick actually clarified this in a 1988 editorial, when you look at people with type 1 through 4 skin, they all, to Fitzpatrick, look white. 1 through 4 is all white skin. That is Fitzpatrick's scale itself. It's only after tanning or after burning that the color changes. And so I think what has happened inexplicably is that everyone has turned the tan scale, what skin looks like after tanning, as a visual analog. I don't know how this happened. My best estimation is that these colors from Fitzpatrick's editorial of what tan skin looks like is the colors that everyone uses. Though I've found many images on the internet that show different types of Fitzpatrick coloration, like this one from the bottom is from the Australian Government Radiation Safety Office. Type 1 is yellow in that particular case. There is a lot of problems and imposition that comes about from doing this. I think getting rid of Fitzpatrick as a visual analog scale would make a lot of sense. But I think in context, and I think also remember that type 1 through 4 was literally white skin, all the same before tanning. So something to keep in mind. 5 and 6 were added later, as Alice said. Now, there are other scales beyond the Fitzpatrick that are visual scales, and we need to consider context when thinking about them. There are several. Some are cosmetics focused. Others are, as Ellis said, potentially really powerful for helping reduce bias in AI. One thing to note, there's also a type of scale introduced by Dr. Taylor in dermatology. Context really matters here. The purpose of that scale was that people who have pigmented skin tend to have really significant hyperpigmentation after they have a rash. And the degree of hyperpigmentation matters, and that's a type of skin type that you would care about. So in that setting, the hyperpigmentation scale makes a lot of sense, but applying it for other cases may not make so much sense. I think as one of the kind of outputs of this meeting, using subjective skin color scales in the right context makes sense. So using it to ensure adequate enrollment of study subjects in a way that's much more objective than just saying dark. That makes a lot of sense. But what you perceive from facial color scales when applying subjective scale, does that actually apply to the skin optical properties? If we're going to use skin optical properties as a calibration target of some sort, that may not make so much sense. So we've talked a lot about color abstractly at this meeting. I just want to talk a little bit about how you objectively define it. The CIE 1976 standard is a 3-parameter approach designed to be uniform and mimic human vision. You can map any color you like into this 3-dimensional space. The z-axis is brightness from 0 to 100, the L star, and the L equals 0 plane is this green to red range in A and blue to yellow in B. You can plot this in polar coordinates as well. Take the L equals 0 plane and grab a hue angle and a chroma. These are exactly the same thing, just mathematical transformations of each other. We can take any color scale and actually plot it in the LAB space. I think, what exactly are the LAB values of the evolution scale? Hard to know. There was one study by Perkin-Elmer, which said they actually took the tiles and did a spectrophotometry analysis to extract LAB from that. And so this is a visualization of their data. And really, you can look at it in 3D, or you can look at it in 2 dimensions, the LB plane, the AB plane, the LA plane. Thinking about projecting into 2 dimensions brings us to individual typology angle, which is the ITA index that a lot of people have talked about and is in the literature a lot. It was introduced by L'Oreal back in 1991 by Chardon et al. As a measure of pigmentation in Caucasian volunteers. Similar to the Fitzpatrick scale, the original scale of ITA was white people, Caucasian people. Chardon proposed plotting the lower back sun-protected LAB values in the LB plane, defined ITA as the angle that your color coordinate makes with the L equals 50 horizon, and suggested that this banana curve represents the limits of typical values in the LB plane, and defined bins that vary from very light to brown based on these individual cutoff angles of 55, 41, 28, 10. And these are up to debate, I think. If we're going to be applying this, what are the appropriate bins to use? It's a reasonable question. I'll also point out there is a little bit of inconsistency in how ITA is defined. The original paper, Chardon, they specifically said A is not included. The redness parameter is not included in our analysis. Perhaps in the future we should include it. And recently some have included it by including C, the chroma parameter in the denominator of ITA. This has been a way to maybe incorporate a slightly different look into ITA. So there are different definitions of it. So in 2013, there was this team at L'Oreal that extended the work of Chardon. This is the Delbino publication in 2013. Shows ITA in 3,500 women across the globe. Added bin 6 to make it a 6 bin scale at -30 degrees. And color was measured in women on sun-exposed facial skin. That may explain why only one of the 3,500 subjects was in the very light category when you look closely at the data. You could actually use that LB plane to map all the various color scales that we have. And these are different color scales mapped here, Fitzpatrick, although I really don't like using a visual Fitzpatrick scale. I put it here just because everyone uses it. The Monk scale, the Massey scale. You can see, as Ellis said, the Massey scale goes into the -B. It has blue hues at the higher end. So does von Luschen, by the way. And so considering these different scales in this general map of ITA may be a useful way for us to just gut check and make sure that we're on the same page in terms of what these color scales mean and how to interpret them. Seeing how those scales go outside the range of the banana curve, you may ask yourself, what kind of ITAs do you encounter in real world practice beyond the work of Delbino, which proposed that banana scale? So there was a study by Wilkes in 2015, 556 South African adults. They compared ITA to a Mexameter melanin index based on inner arm measures. And you can download their, and you can see here what the values range up to an ITA of like 72. Shao et al. Did a separate study. They have a study of 1,000 subjects. You can download their LAB values across multiple skin sites. And you can see that on the cheek, the values that they have go outside of the Delbino banana curve. And furthermore, you can see the ITA category depends on measurement site. So, you know, it's not this melanin index that's universal for a person. It depends on where you measure it. I think the one thing to take note of with the Wilkes site is that they compared ITA to melanin index. That's not the first study to do this. There is literature to suggest actually ITA could be a surrogate for melanin content, which is why I think a lot of people are interested in it from the perspective of pulse oximetry. Indeed, Zonios, in a study in 2001, they compared melanin concentration derived from spectroscopy versus ITA in several subjects with varied skin type and undergoing tanning. They found this really nice linear correlation between ITA and melanin index. So perhaps ITA is a surrogate for melanin. Delbino had a similar result where they used samples from breast reduction surgery. They took samples ex vivo, they labeled them histologically, they did HPLC on them. They also found a linear relationship between melanin content and ITA, though I would say that at the darker region, there may be a little bit more noise there. So I don't know how valid the results are across the full spectrum of pigmentation. I'll also point out that ITA already is part of ISO standards. It is, because it's a melanin surrogate, thought to be a melanin surrogate, it is maybe tempting to think about it that way. And the precedent for it is that it is included in ISO standards for studies of sunscreen. There's actually published equations for estimating minimal erythritol dose from ITA when you look at ITA as a continuous variable. So I think using it as a continuous variable makes a lot of sense. It is a continuous variable and human pigmentation is continuous. But binning can also be advantageous, and we, Alice talked about how people like to bin things in 6 category groups, and so you might say, does the ITA bins that are defined by Delbino, do they correlate with the Fitzpatrick scale? The study by Wilkes from 556 patients or subjects in South Africa, they showed a very strong correlation between the bins of ITA and the bins of Fitzpatrick. However, in a recent photomedicine unit study out at in Michigan, where the Fitzpatrick scale is defined by surveys and ITA is measured with a colorimeter, it's not so clear. The 6-point scales don't exactly match up. At the extremes, maybe they do. 5 and 6 in Fitzpatrick and 5 and 6 in Delbino, and the Delbino scales do correlate, but it's not a one-to-one correlation. In the Open Oximetry Equiox study data that I've been fortunate enough to be a part of, and I think Carolyn for sharing this data with me and acquiring all this data, the results are actually quite different. And I think really instructive because this is data in critically ill patients, whereas most of what we see in colorimetry is from cosmetics, and so it's adult healthy subjects. It's not obvious that in the critically ill, these results and these values have the same meaning. And indeed, here, if there's not a clear correlation between ITA bin and Fitzpatrick scale, you can have a subject with a given Fitzpatrick scale spanning multiple ITA groups and vice versa. We also saw similar issues in our controlled hypoxia subjects here in the Open Ox data set, where you have a spread of ITA values that's more pronounced at certain sites. That may imply that certain sites are actually just harder to measure, like the back of the earlobe had a lot of variation. It may just be a technical challenge to make that measurement. But sure enough, ITA at a given range of Fitzpatrick types shows some variation. And this again, sampling the 133 critically ill subjects that I've gotten a chance to analyze so far from the EQUAC study, looking at ITA measured at dorsal fingertip joint and other sites. This prelim analysis shows that ITA between different sites shows different levels of correlation and offset, and whether these differences are due to challenges of data acquisition or reflect true physiological differences. I think those are important questions that we still don't know the answer to. This is that same data, now just comparing inner arm to other sites. Again, the prelim analysis to me suggests that ITA measured at different sites in the same critically ill person may not correlate so well to each other. I want to point out a really important limitation about ITA. ITA is not color. ITA is a single parameter. Color requires 3 parameters. So for a single ITA value, many different colors are possible. Every color that you see in this block has an ITA of 0. And here we can plot lines of constant ITA. Here's a line of 60 ITA, a line of 40 ITA, a line of 0 ITA, a line of negative 45 ITA, all plotted in LB plane, looking in this Delbino banana curve to indicate that we're seeing real data. Even there, you can see variation in these colors. So it's really important that when we create kind of these abstract notions like ITA, that we don't forget that they don't necessarily map neatly to a conception that we have in our mind of what someone's pigmentation is. Another caution that I really want to throw out there, if we're thinking about ITA as a standard for an index of melanin that we can use to, let's say, correct or adjust the pulse oximeter signal, we need to be sure that ITA really is affected just by melanin alone. This study from Stamatis et al., they use spectroscopy to extract chromophores like oxyhemoglobin, deoxyhemoglobin on the volar forearm. And they did an inclusion study on the arm where they did a blood pressure cuff inclusion. What they found was that what changes when you do that is the deoxyhemoglobin extracted signal. That makes sense. But what was surprising was that as deoxyhemoglobin went down, as deoxyhemoglobin increased, the ITA decreased. So if this is this index of melanin and melanin is staying constant, then what's going on here? There must be something else that's contributing to ITA. And it speaks to the potential role of actual tissue perfusion, not the perfusion index, actual tissue perfusion, and how that may impact ITA, which may have really profound implications on using ITA as some sort of surrogate or correction factor for pigmentation. So, I've talked a lot of background. I still haven't even told you how do you make these measurements. One way to do it is to use spectrophotometers. These measure wavelength-dependent changes in reflected light. There are research-grade approaches like this one, which is a 100-patient calibration set performed by NIST. You can actually download these 100 diffuse reflectance spectra. They range from UV all the way up to 2,500 nanometers. It's a really beautiful data set. I have a setup like this in lab that doesn't go quite as far, but uses integrating spheres and ocean optic spectrometers, and that's a pretty standard thing that people do in optics. There are commercial options like the CM700D. This is from Konica Minolta. This is a reflectance curve that I measured for my inner arm, and it matches nicely in the range of 400 to 1700 with the average NIST signal. And you can use software to extract LAB coordinates. But I want to point out something important. When you use this tool, you have to make a choice about what the aperture is that you're using when making this measurement. And when you extract color parameters, you have to make a choice about what the illuminant is. Is it C? Is it D65? And the observer angle. Is it 2 degrees? Is it 10 degrees? If, as a result of this meeting, we decide that diffuse reflectance spectroscopy is a general tool that we should ask that labs that do validation studies use, we need to make sure that we all agree on what the aperture is and what the observer is and what the angle is. These numbers matter for allowing us to compare studies relative to each other. And I say this not because I think that that's the right answer. I just say, if this is the way we go, we have to be standardized about it. In addition to color coordinates, you can use reflectance scripts to extract other physiologically meaningful parameters, for example, melanin index. And there are different approaches to doing this. Area under the curve is one, the slope of the log of the signal from red to infrared is another. Wim will probably talk about a really clever idea he has put in the literature around taking just the reflectance at the short wavelength of blue, where you overrepresent absorption by melanin, and therefore, that reflectance should kind of overrepresent the melanin signal. I think that's a really smart idea. There are other options, right? There are these narrowband devices called tristimulus devices. Tristimulus is intended to imply that we're mimicking the red, green, blue ability of your eye to interpret color. One of them is the Delphin, and basically you're just subsampling that diffuse reflectance spectra across a narrow wavelength. And then there's the Courage and the NIX Pro. These are white light LEDs, and these guys with filters, and these guys use red, green, blue LEDs. There are big cost differences between these devices. I have all of them in lab, and we're trying to see how they compare to each other. The NIX is $400, and the other ones are about 10 times that cost, or upwards of that. Also want to point out there's a whole other class of narrowband devices called narrowband spectrometers, like the Mexameter. They do not use red, green, blue light sources. They use green, red, and NIR. And something that's really interesting as you think about Dr. Bickler's presentation, where he showed how the pulse oximeter signal actually is made, there is an IR to red ratio that's being used to extract melanin index. So the Mexameter is actually using light at the wavelengths that we use in pulse oximetry to extract this melanin index, which we all think might or may be relevant as we think about standards. And if I have a chance, I'll show you kind of how that may play a role into the R value in pulse oximetry. This is not an extensive list of all the ways you can measure skin tone or skin optical properties. Wim also has proposed some really interesting stuff where you use thermal changes in response to absorption of light. He may talk about that, so I'm not going to go into that. There's also, really interesting biophotonics approaches using spatial frequency domain imaging, where you can actually extract US prime and mu A directly. And from the perspective of global health, are there low-cost options for doing this? I think Daniel probably has a lot of expertise in this question, because I'm probably sure you use these sensors from ALM or ASM or whatever the AS7341 sensor is. But this is a $16 sensor you can buy in Adafruit. I have one of them. You can build your own little spectrophotometer. How well does it work compared to the $400 NIX or the $20,000 Konica or the $5,000 Delphin? Those are questions that are unresolved and I think really worth exploring. There are some studies that have compared colorimeters to each other, but they're very limited in my review. So I'll just share the data from the Equiox project, where you can compare diffuse reflectance spectrophotometry with the Konica against the Delphin in 133 subjects that are critically ill. Some of the sites show stronger agreement than others, like the dorsal DIP. Some sites don't show such strong agreement. That may reflect challenges in getting measurement sites measured consistently across different devices. I think a lot more work is needed to validate these devices against each other. And again, this is just very prelim data that I'm sharing. I want to point out something that I was very surprised to see in the prelim data analysis, which is, and Ellis alluded to this, right, that L star seems to be a strong predictor in the color scales and subjective color scales. Well, L star seems to be a really strong predictor in this continuous ITA variable too. ITA is very tightly bound to the value of L star, even though ITA is a combination of L star and V. This is a real surprise. Initially, I thought I must be doing something wrong, or the data somehow is funny. And so maybe can we find another way to validate this? Looking at that Shao study that I told you about with 1,000 subjects from where LAB values are measured, shows the exact same relationship. ITA strongly bound to L star. So again, when we kind of create this abstract notion of ITA, it's melanin index, maybe it's just a brightness. It's really, I think this is very interesting and needs to be looked at deeper, but suggests some limitations in what these indices may tell us. Another interesting result, when you extract the red, green, or blue channel from the expected color from the Konica Minolta, the relationship between ITA and any one of those red, green, or blue channels is incredibly strong. And I wonder if that suggests that R, G, and B themselves are correlated to each other. I think there's a lot more that needs to be thought about as we think about this rich data set that we have. So a few parting thoughts. One thing, another point about dermatology, whether you're using skin color scales or objective devices, I want everyone in the room who's not a dermatologist to keep in mind that skin pigmentation is not uniform. You can have grayish blue pigmentation affecting the lower back. Maybe that's where the blue scales that you see in some of the color scales come from, because people noticed that as they looked around the world. This is dermal melanocytosis. You can have it affecting the forehead and cheek with the nevus iota. There are actually normal lines of pigmentary demarcation called void future lines that you see in people on a regular basis in clinic. And these are normal. They're not pathological states. This is just what people look like when you look close. You also have to keep in mind that pigmentary mosaicism exists. You have areas of skin that just fundamentally have different pigmentation than others. That's normal. And whatever standard we apply, I just urge everyone in the room to keep in mind that we have to, as we increase diversity in studies, you will see people like this in the studies, and it's important not to exclude them from the protocols, but include them so that we capture the full spectrum of the wide diversity of human pigmentation. There's many limitations potentially to talk about. I think primarily just keep in mind a lot of the colorimetry data and research is in healthy adult subjects from the perspective of cosmetics. Does it apply in critically ill people? I don't know. Does it apply in children? I think the data from Stanford is really interesting. This is uncharted territory. ITA is not color. ITA may not just be melanin. It may relate to perfusion as well. ITA may just be very strongly related to L-star or single values. And I do think from a standards perspective, using subjective scales for inclusion and diversity of clinical trials makes a lot of sense. But if the optical property is what you're after, you may not get there through subjective scales, and you may not get there through colorimetry either. You may need more sophisticated methods to actually extract those properties. I'll finish by saying that my dream from a research perspective is that we get access to the raw data. What is actually happening to the AC signal? What's happening to the DC signal? I have a hack workaround where I've taken pulse oximeters apart and I've put on power meters, and I can actually measure the DC signal and see it, but that's not very effective. And I would love to be able to get access to the raw data so we can actually see what's going on. I want to thank everyone for giving me a chance to speak and for all the work that's going on today. It's really important. And I'm happy to talk offline by email. I'm sure I've said things that I can learn from, and if you want to correct anything I've said, please email me and let me know.
So next we have Dr. Sandhya Vasudevan, who is a CDRH staff fellow in the Division of Biomedical Physics at the US FDA with a strong background in near-infrared spectroscopy and tissue optics. Dr. Vasudevan's current research primarily focuses on advancing regulatory science tools for assessing pulse oximeter performance in a diverse population and studying the effects of skin pigmentation on optical diagnostic devices. Dr. Vasudevan, and please correct me if I pronounced your name wrong. Thank you.
No, it's correct. Thank you. Thank you for the introduction. So hi, everyone. I'm Sandhya Vasudevan, and today I'm going to be talking about melanometers, which are optical devices, as you've heard in the previous talk, to objectively quantify skin pigmentation. And we'll be talking about how feasible these devices are for use in pulse oximeter studies. And some of you who have been to the SPI conference earlier in January might already have heard or seen some of these slides, as my colleague Bill did a great job of presenting a lot of this work at the SPI conference. Having said that, let's jump into the talk. So as we've heard over yesterday and today, we do think that skin pigmentation is considered to be the most likely cause of the ethnic/racial bias seen in pulse oximetry measurements. And this is mostly tied to the epidermal melanin, which, as we can see in this histological slide, is shown to change with racial groups or ethnic classifications. Now, epidermal melanin is a strong red near-infrared absorber, as you can see in this absorption spectra, which compares blood and melanin absorption. Melanin does absorb strongly at specifically the pulse oximeter wavelengths at 660 and 940 nanometers. For example, if you look at 660 nanometers, the absorption of epidermal melanin is high enough to reduce the detected light by up to 40% per pass through the epidermis. And on the right-hand side, there is another interesting plot that compares reflectance between different Fitzpatrick type. And you can see how based on the skin color, the reflectance does get affected and attenuates a lot. Other optical technologies, diagnostic devices like cerebral oximeters, hyperspectral imaging, photoacoustic imaging has also shown the impact of epidermal melanin on some of their measurements. The impact of epidermal melanin can also depend on the body site under consideration. As we have heard in some of the previous talks, pigmentation is often assessed at locations like forehead and forearm, which have much more pigmentation compared to the common pulse oximetry site, which is the fingernail or palm of finger. The pulse oximetry site not just has a lower level of melanin, the variability of melanin between patients within a heterogeneous population is also much lower when you consider the site. So we'll start by discussing about some of the common skin pigmentation assessment method used in pulse oximeter studies. In about 32 or more retrospective pulse oximetry studies, race or ethnic skin self-identification has been used to categorize skin pigmentation. And as we have all heard in the previous talks, and we know that these are very subjective, qualitative approaches, and each categories are so broad and it lacks the accuracy or specificity required to ensure any statistical validity. Another approach which we heard a lot in Dr. Monk's talk and also in Leo's talk is the Fitzpatrick skin phototype, which I'm not going to talk again about it. We have criticized this method well enough. So I just wanted to also show that we also did see how in the published space, there's different colors used to represent the Fitzpatrick scales, and it is not well standardized. And there's a lot of lack of agreement in how this color looks like. And the other approach would be to use color scales, which has been infrequently used in some of the pulse oximeter studies. And I've just, again, shown some examples over here, which includes the Massey-Martin scale, the Munsell scale, the von Luschan skin scale, and the Monk skin tone. And the Monk scale we already had a good discussion on that. I would like to just point out that what stands most interesting about the Monk skin tone to us is how we can establish, it is well established to the standardized color space because it can be digitally expressed in an LAB space or an RGB form. So it is nice to see that the color can be expressed as a number as well. Now, theoretically, there should be lower variance as these color charts have been standardized, but access to validated charts is a limitation. As we saw in the von Luschan scale, how Dr. Monk pointed out that it's originally in the form of tiles, but it is hard to get an access of the standard version. And again, these are subjective approaches, so we have to keep in mind that they do have the common subjective errors, which includes interoperator bias and some lack of reliability, as it is subjective. Now, we've seen a lot of publications criticizing the overall use of subjective methods to categorize skin pigmentation. Some call them a limiting factor in clinical studies, how they are often used as a surrogate for the actual epidermal melanin content, which reflects skin pigmentation. The categories are often too blunt and broad. And some studies have gone to the extent of saying that the use of subjective scales should stop altogether. So what does that mean? Like, as we have already discussed, these subjective errors just have perceptual errors, interoperator variability, lack of reliability, are non-standardized. So what's the other method? It's the objective methods, which includes either the use of optical devices, which use colorimetry or spectroscopy, which are the non-invasive technique of categorizing pigmentation, or the use of more invasive techniques like biopsy. And I'm not suggesting use biopsy or invasive methods for clinical methods. This is mostly would be a gold standard technique of determining melanin. So the limitations of specifically melanometry is that there is not a proper understanding on how repeatable these devices are, how well these different kinds of devices agree between each other, And what kind of correlation do they show to these gold standard approaches like biopsy and HPLC? So what we did was to kind of investigate that. We decided to do a meticulous literature review to evaluate the feasibility of melanometers to assess skin pigmentation and if they can be used in pulse oximeter studies. So we focused on two areas. One was to identify technical approaches adopted by commercial melanometers, and two was to see what studies report their accuracy, repeatability, and how reliable they are. So this is just a quick overview of how many studies we looked at, what kind of studies we looked at. We looked at correlation studies and repeatability studies, and the key areas we focused on was how these devices compare with subjective methods like Fitzpatrick, how well they agreed between each other, intermelanometer comparison, accuracy with respect to some of the invasive gold standard approaches, effects of confounding factors, which is hemoglobin, so effects of melanin hemoglobin crosstalk on accuracy of these devices, and repeatability, which can include intra-observer repeatability, inter-observer, and inter-instrument repeatability. So for all the studies we looked at, the correlation was expressed as strong, or the repeatability was expressed as high based on the conditionality listed in the slide, in the bottom of the slide. So we'll start with a brief overview of some of these melanometers. So the melanometers are essentially reflectance-based devices. They acquire visible near-infrared reflectance, and they have broad applications in the fields of dermatology, anthropology, and cosmetics. Most of the commercial devices come in handheld forms, which use spectroscopy or colorimetry. Examples of a couple of devices that we bought in a lab to further this research are shown on the right-hand side. And if you look at these probes, you can see that their measurement area is small enough that we can measure skin pigmentation at the pulse oximeter side, the palm of finger. Now, for methods, these devices can be broadly classified based on how they acquire data, how they would process data, and what kind of outputs they would deliver. So we'll start by quickly going through the narrowband reflectance devices. Now, these are devices that acquire data at 2 to 3 wavelengths in the visible near-infrared range, and they calculate an index called the melanin index. And the equation commonly used is a log ratio form of reflectance. Now, the strategy behind this equation can be traced to several foundational publications, where a score of melanin or an index of melanin has been calculated as a slope of a straight line fitted in a wavelength range between 600 and 800 nanometers. However, there are different commercial devices. So the wavelengths used by these manufacturers, or the equations used by the manufacturers, do vary between devices. And if you look at these two equations, even the scale in which the final metric is outputted does change between devices. Other spectroscopic devices would be broadband reflectance devices, which acquires reflectance at many more wavelengths in the visible NIR range. And access to all this multispectral data with broadband reflectance devices lets us calculate custom derived metrics, which can use short wavelengths, which helps in optimizing epidermal selectivity. The other category of devices, other than the spectroscopic devices that we just discussed about, would be colorimetric devices. So the previous talk, Leo has done a great job in actually going through this, so I'm not going to go through this in great detail, but just wanted to mention that the color quantified in colorimeters is a perception of the color. It's how it appears to the human eye. And this can be expressed in an LAB space, which is a linearized version to express these color values. And these LAB values can be converted into ITA values, which was also discussed, which has been previously categorized by Chardin and Delbino into 6 different categories, ranging from very light to dark. So we have also looked at how the monk skin tone looks in the LAB space, which you also saw in the previous slide. I just wanted to kind of also show how the monk skin tone changes with ITA on the right hand side. So a couple of things that we noticed is that the monk skin tone is not quite linear with the ITA space. It has kind of a non-linear distribution, as you can see over here. And we also saw that it's kind of sparse in the intermediate skin tones. And something else that I wanted to point out was that we looked at a couple of published ITA data in literature. And we did see that some of these low and very high monk skin tone was not well represented in some of the published data, but that could also be if they did not include a heterogeneous enough population. But some of these lower tones was not well reflected in these studies that I've listed over here. Now that we have an overview of the devices, we will go to the core of the talk, which is the Melanometer performance data that we compiled after our literature review. So we'll start with what we found when looking at comparisons between objective and subjective approaches. So here you would see a compiled results of the correlation data of melanometers versus the Fitzpatrick skin phototype. And some examples of correlations is now shown on the right-hand side. What we saw is moderate but very variable correlation between melanometers and Fitzpatrick. So strong correlation was only observed in about 28% of the results. So there was a lot of variability in correlation, and it was not a high percent of the results showing the strong correlation. Next, we looked at how these devices compare between each other. So for that, we compiled all the correlation results published out there between different devices. And an example of a correlation result between the colorimeter CL400 and the Mexameter is shown on the right-hand side. We saw strong correlation in about 76% of our compiled results. And we also saw that the colorimeters and the narrowband systems, which have different processing and acquisition strategies, were also well correlated between each other. The other important part that we looked at was the repeatability of these devices. So we compiled the intra-observer, inter-observer, and inter-instrument repeatability for several of these devices that has been published. And we saw high repeatability for most of these cases. When we compared the repeatability of the objective techniques to subjective approaches, we did see, as expected, that these objective devices had much higher repeatability than the subjective approaches. Some of the confounders that we think can impact the repeatability of these devices could be the body site where this measurement is acquired, the contact pressure applied when acquiring the data, the erythema or the flushing of the skin, and orthostatic changes, ambient temperature. One of the problems that we came across when looking through literature was the impact of hemoglobin on the melanin index that is quantified by these instruments. So if you look at, again, these absorption spectra comparisons between blood and melanin, from 600 to 1,000 nanometers, they follow a similar trend. So there's a lot of crosstalk between the melanin and hemoglobin absorption, which makes it difficult for some of these devices to accurately separate them out, which is what we saw in a couple of these studies, and examples have been shown on the right-hand side. You can see how for this first case, the erythema index increases with the melanin index. And again, for the right-hand side, you can see a similar correlation between A star, which represents erythema, and L star, which represents the darkness of the skin. So both of these studies does show a correlation between erythema and melanin, which is not properly defined. Like, why would darker subjects have higher levels of hemoglobin? So that's clearly shows a crosstalk between these two absorbers affecting some of these outputs. One of the key areas that we were interested in was looking at how these devices compare to the invasive gold standard method. So before we go to those results, let's just quickly go through what are the techniques that we defined as gold standard. One was histology with staining. So there are melanin-specific stains like Fontana Mason and a couple of other stains that have been used in literature to look at the melanin distribution, and different techniques were used to quantify them as an index. And the other option was a high-performance liquid chromatography, which looks at homogeneous tissue samples, and they can quantify not just the total melanin, but also the eumelanin and pheomelanin, the two types of melanin, which was also very interesting. Now, just to be clear, these techniques, I don't suggest them as a technique that can be applied in clinical studies. The primary role of these invasive techniques would be to validate the non-invasive optical devices that we are talking about. So we compiled correlation results of these objective devices with some of these gold standard techniques. And we did see a strong correlation in about 19 out of 32 studies that we looked at. And this was much higher than the strong correlation we saw between melanometers and the subjective approaches like the Fitzpatrick scale. One problem was that there were a limited number of studies, and there was also some variability between the results, which kind of emphasizes that there's definitely a need for validation of these devices with respect to some of these gold standard approaches. Another approach to validating at least the colorimeters would be to use some of the standard color charts like the Pantone skin tone or the X-Rite color checker. These are some standard color charts that's available. They can be used in combination with a standard illuminant like the D65 to validate or calibrate these devices. And such techniques have been seen in the literature as being used to study repeatability and inter-device performance of colorimeters. So one approach would be to compare the measured color patch value by a given device to a standard value as measured with a gold standard sensing device. So to conclude, we do see that melanometers can provide a non-invasive estimate of epidermal melanin content and do show more accuracy than some of the commonly used subjective approaches. Why? Because we did see that they show high repeatability, they show good inter-device consistency, and a strong correlation to gold standard techniques. There is although based on a literature review, we do think that there is a need for more rigorous validation studies, and there's definitely room for improvement in a lot of these devices. Overall, it does seem like a promising tool to be applied in pulse oximetry studies to assess skin pigmentation. As future directions to improve melanometer performance, some things that can be done is to use short wavelengths, which I'm sure that Wim after me would talk about how useful the short wavelengths can be to reduce blood melanin crosstalk. The second would be to revise design to improve sensitivity, specifically sensitivity with respect to the pulse oximeter site, which is the fingernail bed. Also, other than using the other options would be to look at other potential candidates that can quantify melanin, like photoacoustics or spatial frequency domain imaging, which have tissue depth selective capability. Now, for validation and standardization of melanometers, invasive approaches is something that we looked at, but another idea would be to use non-invasive references like confocal microscopy, multiphoton imaging, or OCT. And we do see that standardized best practices for melanometer validation study would be of great use to validate these devices. Thank you for listening to my talk. I would like to acknowledge my team at FDA who contributed greatly to this work, and special thanks to Dr. Wei Chung, who is our color expert at DITSER, who educated us a lot on colorimeters. Thank you all for listening.
Great. And so next we have Dr. Wim Verkroesje. Just so you're aware of his background, Dr. Verkroesje conducted a PhD on laser therapy of vascular anomalies in 1998 at the University of Amsterdam in the Netherlands. He continued in a postdoctoral position in dermatologic applications of light at the Beckman Laser Institute in Irvine, California, with a focus on diagnostics rather than therapy.
Thank you very much for inviting me for the introduction. First of all, I think it's really great that you've brought us all together in contact with Leo, with Alice, with everybody working in this team, because I really think we have some momentum going. And a lot of my thunder has been stolen because I agreed with Alice, with Leo, and what I'm going to say is just a little nuance and perhaps saying the same thing in a slightly different way. So pigmentation measurement method, which I call PMM here in the context of pulse oximetry. I'll give a short introduction, and that's where my thunder has been stolen, but I'll also show some results of the 2 studies, and one of them is still going on. The motivation is the standardization, of course, but in view of the discussion we had yesterday about the root causes of the bias in pulse oximetry, I think it's completely open still whether pigmentation is the root cause or a confounder. I don't know, but either way, if we have a proper tool to measure pigmentation, we can find out if it is the root cause quicker, and if it is not, we will also be able to find that out quicker. So that is a little bit motivation. So what we think PMM should have, they should be accurate, precise, and sensitive. Most of all, repeatable and reproducible between operators within operators. Ideally measure just melanin, not blood, and we would prefer a linear scale, which makes the inclusion criteria less complex. I also think an ambiguity is important. The melanin index, as I will tell later on, has been used by a lot of different devices, different definitions, and as a scientist who tends to be a little puritanical, I really hate that. If we talk about the melanin index, we should not have to tell which device it is. Another disadvantage is that they sometimes have a black box. You really have to look for the formula. And what also important is I think in a PMM that there should not be a wiggle room. For example, if you change the orthostatic conditions or warm at the hand, it should not change the value. But most of all, it should be practical. I think, as the previous talker, I forgot your name, I'm sorry, has indicated that HPLC methods, not invasive methods, are not practical. It should require minimal training, and it should be able to measure on POX sites, on pulse oximetry sites. So accurate, precise, and sensitive, unambiguous, and practical. So some of them that are available to us as subjective methods have been mentioned already. Objective methods, I call them EM meters because typically they give an erythema index and a melanin index, and RS devices and colorimeters is a different group. They're slightly different. Here I give some of the scales that are used, 1 to 6, 1 to 36. We can mention profusely. Skin tone, the melanin index varies. Sometimes has a scale from 1 to 2000, sometimes from 1 to 20. And here this has been talked about as well. And the 1/400 method is a research method that has been mentioned previously as well. Okay, this is a slide that may be interesting if you want to know a little bit how they work. These curves have been shown, the absorption curves, hemoglobin, oxyhemoglobin, and melanin, and water should be there too. And then here we have the bandwidth where they measure erythema and melanin meters. They measure typically in the yellow, red, and the near infrared. Colorimetry uses 3 bands, just like an RGB camera, so it covers the visible spectrum. And spectrometry measures the ones that we use, at least in the visible spectrum, at increments of 10 nanometers. And this is how then the measurements, the core measurements, are translated into a melanin index, erythema index, and then finally, typically, they are mapped onto a 6-value scale. And I really do not like to call them Fitzpatrick scale anymore because very often they have nothing to do with the Fitzpatrick original intention at all. They just have a 6-value scale, and that's it. And that's why I like to call them 6-value scales instead of Fitzpatrick, just to avoid the confusion. And the ITA also is mapped onto a 6-value scale, which I do not call the Fitzpatrick. So if we go to the to determinations of skin color, we have 2 dominant chromophores, blood and melanin. And of course, you can talk about eopheomelanin, oxyhemoglobin, deoxyhemoglobin, and other derivatives like methemoglobin. But just as important is the depth of these chromophores, as Leo pointed out. Dermal scattering is important, and the blood vessel diameter is very important. The same amount of blood distributed in small vessels looks much, much redder than that same amount of blood in a couple of larger vessels. That's what I learned in the laser therapy of vascular lesions and laser dermatology at the Beckman Laser Institute. So how many parameters do we need to describe the pigmentation? And Leo has thought and explained a lot about it already. I think this is on the left, the complexity of the skin. And really, we have tons and tons of parameters there. The skin is complex. And if you measure the reflecting spectrum, you have already thrown away a lot of information. So you have fewer degrees of freedom. And the spectrum is not unique for skin geometry. You can have the same reflecting spectrum to the skin, but they really will have a different melanin concentration if the depth, for example, is different of other chromophores. Color is even a more simplification. You only have 3 degrees of freedom, and then the ITA is 1 degree of freedom. The melanin index is also 1 degree of freedom. So less unique, but 1 degree of freedom to describe what we have at hand here, I think seems practical and descriptive enough. And that's also what Leo found in his comparisons of all the different metrics. Okay, one word on metamerism. Metamerism is typically explained with, if you're in the morning, you're grabbing 2 socks, you think they're both dark blue, and then you come outside in daylight and one of them turns out to be dark green and the other one turns out to be dark blue. So under one illumination color, they are exactly the same color. With a different color, they look different. And that is also possible with skin. Metamerism occurs if the underlying chromophores have different spectra. And that could be the skin as blood and melanin as chromophores, but the ink and printed color scales have different spectra. So this is at risk for metamerism. That is something to be aware of. And I've included the Monk scale here because that's a question I still want to ask Dr. Monk. If perhaps this scale to me looks like it's more black to white and has fewer red tones, that might be an advantage in terms of metamerism, in terms of assessing, and thus less dependent on illumination color. So now let me move to 2 studies that we did. Study 1 has 21 subjects included, and the focus was on exploring and comparing different methods. We also looked at how the skin color varies across the body, including the pulse oximeter sites. We used the Konica Minolta spectrophotometer and the Maxameter device. And subjective methods included the 3 scales, but also the Fitzpatrick questionnaire, the old-fashioned Fitzpatrick questionnaire. Study 2 is still ongoing. We included 12 subjects so far, and the focus is on repeatability and reproducibility of those methods, precision, the impact of blood on the melanin index that has been mentioned already, the pigmentation on the sides of the fingers we also measure instead of just on the nail in the palm of the finger, because we have heard that if people have nail polish on, people tend to just turn the pulse oximeter by 90 degrees. And then, of course, the sides of the fingers become relevant. Yeah, these are some of the devices that we used. And I will also show some attempts to do some standardized photography as an alternative method for colorimetry. This is what it looks like in the lab. We have the Pantone scale, the Van Lucian scale, the Fitzpatrick scale here, or one of the Fitzpatrick scales that we found. Here are the devices. This is an illumination source. We wanted to do the color assessment with the scales in the best possible way. So we have standardized traceable illuminant, which is quite expensive, but we thought let's give it a try. Otherwise, we will have something in between the worst case and the best case. So this is supposed to be the best case. Something on color matching scales. We included the Fitzpatrick or a Fitzpatrick color scale. We do not like it because it's not defined. There are many varieties. The Van Lucian scale is somewhat better defined. Wikipedia is not a device source, but at least we have not found a lot of different definitions. The Pantone scale is nice because it is well defined and also factory printed. So each person that will buy that color scale will have the same scale actually in their hands. And then I would like to learn a lot more about the Monk's skin tone scale. I haven't had time yet, but that to me looks like indeed addressing the main disadvantages that we find in these scales. That Black people, black skin is not really covered by these scales, and also light skin, ironically. So these are some of the objective devices used. I've pointed out here that the probes for the Maximeter and the skin pigmentation analyzer for the SPA, they have the same probe. It seems you just push it on the skin and it measures. They have quite narrow openings actually, which if you have a lot of freckles on the skin, for example, that may be an issue and you may want to average out those freckles. Leo already pointed out the 10 millimeter diameter of the aperture of the punica minota may not be good enough, but we have to agree on that. It's an expensive device, the spectrophotometer, but colorimetry, as you pointed out, can be much less expensive than this spectrophotometer. And the big advantage of colorimetry is that it has had standardization for several decades already, and it has been a stable standard, so it's a mature technology. Here, I'd like to point out that the main reason I wanted to include the skin pigmentation analyzer is that it's a device by the same company, Courage and Casata, and they both produce a melanin index on completely different scales, and that just drives me nuts, to be honest. So let me now go to some results of the first study. The focus is on exploring and comparing different methods. So here we can see on the vertical axis 21 subjects, sorted from light skin to darker. On the left, you see here the dorsal arm, ventral arm, forehead, the ala, the nose, and then we see a lighter column in the middle that represents the palmar fingers, and then the slightly darker column right are the nail colors rendered from the LAB values from the device. Then if we map those L and B star values onto the ITA, we get this map. And then if we then map each location onto one of the 6 value scales that we've seen from Dalbino and Chardon, then we see that each subject really covers quite a large range of those bins. 3 to 4 is not strange to find. And that is something that we found interesting actually. So it becomes very important to discuss where we should measure. And another thing that was quite striking from this study is that with all 3 methods or metrics we used, the melanin index, ITA, or 400 method, we find that the finger pads are quite light. Still, dark-skinned people have also on the palmar side darker skin, as you can see here by the 7 darkest subjects, 7 medium, and 7 lightest subjects. With the ITA and the R400, we also found a significant but small gradient from the thumb towards the pinky. And that could be interesting because that could then present an opportunity to use the same person as your own control, where pigmentation is a gradient, a parameter within one individual, where the SpO2 obviously is the same. Of course, you have other parameters like finger size, etc. This was one result. And then on the finger pads, on every location we measured 3 times in a row just to get an average. And on most locations, we did not really see a change from the first, second, and third. But on the finger pads, we really saw, if you look carefully, you can see that each set of 3 measurements tends to go down. And here, the black ones go down. And simultaneously, the erythema index would go up. So basically, we see here that 3 repeated measurements on the finger pads, the erythema index goes up and the melanin index goes down. And then you can wonder which one is a better representation for the melanin index. When you've, after the 3rd, 4th, 5th, or 6th, or is it the first measurement? Then if it's the first measurement, the question comes up, how long should I wait to take another sample for average? And that was actually input for a second study, as we will see later. This slide shows on the vertical axis the 4 subjective methods. So the Fitzpatrick, Pantone, Van Lucian, and here the old-fashioned Fitzpatrick questionnaire. And on the horizontal axis, we have objective metrics like the melanin index from the MX18, and you have to say which melanin index it is, the ITA, and the 1/400. We looked at precision and accuracy and linearity. If you look at these little horizontal thingies in each symbol, that represents the standard deviation from 3 repeated measurements. So the objective methods, they all have very high precision. 3 repeated measurements give a small standard deviation. So if we assume that that is the precision of the objective, we can use the variation in the vertical axis as a measure of imprecision, if you will, for the subjective measurement. And then we find that the Pantone has a slightly better precision than the other ones, and that the questionnaire, looking at all the red lines, really is not correlating at all with the objective measurements. If we look at the linearity, simply looking at the correlation coefficients here, we find that the 1/R400 seems to have the best linearity with the other metrics. The other ones seem to be slightly nonlinear here, as you can see. That linearity is not so surprising. We have seen that in 2009 earlier. And yeah, if you think about which wavelength would best be sampling the melanin, it makes sense to think of the short wavelengths because they only penetrate 100 micron, and the red and infrared wavelengths used by the EM meters, they penetrate the skin millimeters. So then if you only want to look at melanin, it makes sense to use those shorter wavelengths, right? And that's indeed what we found. But on the other hand, it's a single point measurement, so it's not spectroscopic. It's simply using the rationale that more melanin, less reflectance. And that makes it slightly complex, that measurement. And with the EM meters, you have at least 2 points spectroscopy. Let's now move on to the study 2, which is still ongoing. The focus is on repeatability, reproducibility, precision, and also the crossplay between blood and melanin. We included the skin pigmentation analyzer. We also included some level of standardized photography, and subjective methods are very similar, except now we use standardized illumination. So we have 12 subjects, 6 light skin, 6 dark skin. We have 3 color scales. 4 locations were assessed by 3 operators. So the forehead, dorsal arm, temple arm, and inner bicep. We have 3 visits of each subject, just to see how consistent each operator is between each visit. And that allows us to look at the repeatability and the consistency within operators. And also we have 3 operators that are independently, they are not in the same assessing at the same time. That allows us to look at inter-operator consistency. These are some results. The SPA is there for reference. That's a skin pigmentation analyzer. That's the only objective one. You can see that from the first, second to the third visit, it's quite consistent. There are 3 operators doing that measurement with the device. That's also quite consistent. And then these are the first results looking at some of the normalized standard deviations for the color scales. And we can clearly see that they are indeed worse than the objective. Relatively large value for the SPA here is probably due to the fact that we were not quite capable of getting exact the same spot between the visits. So we may have slightly different spots. This is an example of the 12 subjects on the finger pads. So this also shows perhaps or corrects a little bit the impression that the earlier graph gave, that dark-skinned people have lighter, just as light in their palm of fingers as light-skinned people. I think these photographs, all taken under the same condition with fixed camera settings and fixed illumination, shows that that is not true. And if you look carefully here, also you can see that the 7 darker skinned people also on the finger pads have darker skin. This is just one example of a picture where calibration of colorimetry with a relatively cheap RGB camera could be done if you include color scale in the picture. And I think there's even a company that has commercialized this. Leo has that information. And that is an example of how colorimetry could be calibrated and with cheap means, with inexpensive means indeed. So this is an example of the crosstalk between blood and melanin. This is where I put a blood pressure cuff on my arm and measured the melanin index repeatedly. It went up by from 90 to 130 clearly, and that was repeatable. And then the opposite, I slapped my arm with a ruler causing erythema, and then the melanin index went down. Clearly not because of the melanin changing, but clearly because of the crossplay of the blood having an impact on that melanin index measurement. Now, we saw the slight impact of crossplay between blood and melanin on the palm or fingers that I showed earlier. And I was actually expecting to see that again and doing all kinds of perturbations, playing with the measurement frequency, open 25 hertz to very faster measurement. We did ortho on the table, normal pressure probe versus firm pressure probe. And actually there, the effect seems to be negligible. So it looks like the newer version of the Maximeter does not have that same problem as I found many years ago. So there's been an improvement. I do not know exactly what they did, if they changed the algorithms or the wavelengths. But that it also represents actually the challenge that you would have in traceability of that metric. So some other results from study 2 that are not shown here is that I mentioned the pigmentation measurements on the sides of the fingers. I haven't analyzed that. Acclimatization of the subjects to see if that is important. Because in the manual it says let the subjects acclimatize for 20 to 30 minutes. In reality, not a lot of people do that, I think, but still it says it. I will look at repeatability and reproducibility using a gauge R&R method that's designed for Six Sigma analytical approach. And now we'll look at repeatability, reproducibility on the scale of minutes, hours, and weeks. And then for the 4 locations. So now a small note on color scale matching. Within operator consistency is better than between operator consistency, but I was actually relatively surprised that each operator seems to be relatively consistent from visit to visit to visit, from week to week to week. Between operators, it's a lot worse. And this is under the best conditions of having a standardized lamp that is the same every visit. And I'm sure that these factors together will add a lot of imprecision. For example, different illumination conditions, color blindness. 1 in 12 men is colorblind, and I've read that half of them is not really aware of it. And I have a colleague who only learned when he was 25. I have no idea how that will impact the assessment, but I'm sure it has some impact. And this here is an example of, to me, one of the strongest optical illusions. Tiles A and B here are exactly the same level of darkness. And just your brain fills in that this is in the shade of that cylinder, so it must be lighter. And now here, if you connect this tile here, that's one color, but it looks as if it's a gradient. This is just your brain fooling you enormously about the darkness of that skin. And that is also the case, I think, if you have a gradient on in your bicep, for example. The illumination angle will matter, the light intensity will matter. But on the other hand, distinct advantages of color scale matching include low cost, easy access, so it can be easier used in real world studies during convenience sampling. This I've already mentioned, the original Fitzpatrick, and it's also been mentioned by other speakers today. It really, Fitzpatrick is not supposed to test skin color or skin tone. It really was supposed to describe the response to UV. And then these are some, we already showed, these are some examples of the Fitzpatrick color scale that I found. They are illustrations, but they have been used as tools, unfortunately. And then this is also mapping onto a 6-value scale. Really has nothing to do with Fitzpatrick, and we shouldn't call it. These are some of the Fitzpatrick scales that we found, just some, and you can see here that if you look at the ITA, that they overlap quite a bit. So coming to an end, our preferred pigmentation metric is the individual typology angle, because it's relatively, it's well defined, uniquely defined. There's not a lot of discussion. I was a little bit unpleasantly surprised to hear about getting that C value in. I do not like that. Let's keep it simple. It's well established, it's transparent, it's not ambiguous, it's practical, it can be measured with several existing devices with a mature standard. And I would prefer it to be binned then in 10 bins, because the 6 bins are too coarse, I think. And I really like the Monk skin tone scale, because it has the very dark skin and the very light skin better represented. And I think I was quite clear about what I do not like about the melanin index. It has many different definitions, different wavelengths are used. Algorithms are sometimes proprietary, and conclusions, pigmentation across the body varies strongly, 3 to 5 degrees on the 6-value scale. Color matching has relatively low precision, even with expensive standardized illumination. It's about, the standard deviation was about 1 degree on a 6-value scale, so I think that's substantial. And further standardization is cumbersome and expensive if you want to go there. EM meters seem to have improved, but they still have a very poor inherent standardization. And colorimeters, well, that is a field that is relatively mature already, and the challenge is, I think, to make it less expensive. And then some points for discussion. Yeah, what is the root cause of why? Is melanin really the main root cause, or is it just a confounder? And if we put our energies together, we can quickly find out, I hope. And then another point for discussion is where to measure the skin color for inclusion in studies. Should it be the forehead, which is varying across the seasons, or should it be the inner arm? And well, I have my preference, but that's open for discussion. And that was the end of my presentation. Thank you very much.
Next, we have a video recording of a presentation by Dr. Adia Benton, who is a cultural anthropologist with interests in global health, biomedicine, development, humanitarianism, and professional sports. And broadly, Dr. Benton is interested in patterns of inequality and the distribution of and the politics of care in settings socialized for scarcity. This means understanding the political, economic, and historical factors shaping how care is provided in complex humanitarian emergencies and in longer-term development projects like those for health. And co-presenting with Dr. Benton is Dr. Amy Moran-Thomas, who is also a medical anthropologist and professor at MIT, who introduced herself earlier, but feel free to say a few more words. Okay.
So there's meant to be audio. Not that well personally. Yeah.
Hi, I'm Adia Benton, and I'll be presenting a social history of measuring color in medicine, recommendations to a perspective from anthropology of medicine and STS for science and technology studies. Here's a quote from anthropologists Guillermo Yarzun and Andrea Ballestero that you could hear as a frame for this talk that we'll return to at the end. The device's power lies in how it makes visible the links between the establishment of facts and truths and the consequences those have on people's body histories as a result of their sustained use. You can keep that in mind as we dive in. In the summer of 2020, a working appeared to be that racial bias oximetry was a problem, despite the fact that earlier research suggested otherwise. Using the tools of ethnographic analysis, my colleague, medical anthropologist and STS scholar Amy Moran Thomas, helped to bring the biases of the device to public attention. Introducing many doctors to overlook studies in their medical specialties. And since then, a number of clinical studies have demonstrated how prevalent this bias is and the potential negative clinical outcomes. I want to again offer a logical perspective because the solution to address the racial biases is essentially the improved quantification. Because the color scales under discussion originated largely in our discipline, we as anthropologists wrestled with the problems inherent to this respect. One scale promoted as a possible solution at the FDA hearing, for example, was created at the turn of the 20th century by the Austro-Hungarian anthropologist and physician Felix von. He sold chromatic scale kits like these to quantify pigment of diverse populations. These 36 color designations were used in colonial and imperial projects of all kinds, including in his role as a member of the German Society of Eugenics and Racial Hygiene. The example pictured here is from the US Holocaust Museum. Now, we imagine that the FDA was unaware of this history when they recently highlighted von Luschan scales for oximetry testing. So we wanted to call attention to why such histories continue to matter and questions we need to ask when using any color scale. For today, we would like to present a more recent case specific to oximetry. In this case, when skin color quantification was used to investigate, it didn't fix the device errors. In fact, the very opposite happened. Skin color quantification enabled bias and was explicitly used to overlook and dismiss device errors. Using this case, we'll cover 3 topics researchers should be attuned to regardless of what scales they're using. First, potential problems with applying population level models for skin colors and some potential fixes. Second, pathologizing language, producing design error and how to check language. And third, the importance of racial self-identification and its continued use. A 1998 study came out at a time of growing concern about racial bias in oximetry. You can see here. And in this table, we can see that patients with darker skin tones were 3 times as likely as those with lighter skin to get a faulty reading. Group classified as dark experienced a 32% device error rate compared with 11% in the groups classified as light or intermediate. In comparison to those we find today, device technology appears to have gotten better over the past 25 years, but the ratio of errors founded by Soding and colleagues in 2020 is nearly the same. The 1998 data should have been a red flag that the device was not working well equally for everyone.
So we're gonna stop since the audio is very spotty, and luckily Dr. Moran Thomas has the script, and we'll restart, and she'll present this lecture.
And if you could keep the slides playing, actually.
Okay. Sure. Is that okay?
Great.
I'm
Yeah.
sorry for the
Yeah.
technical
Great.
glitch there, but.
Yeah. Or
And-
closed caption.
Yeah, and we can also post these online. Sorry about that. So, not sure, this is playing from Mike's computer.
Yes.
I'm not.
Maybe he could
Okay,
come.
yeah, if you wouldn't mind starting from the beginning. Yeah.
We're not gonna play the audio.
Is there, I just walked away for a second. Would it be easier if?
Yeah, would you like to just read it live, Adia, if possible? The audio.
Sure. I had a feeling that there would be some glitch. And I've, managed to get from the airport. So except I don't know exactly where.
You could restart from the beginning, maybe.
Yeah, I think so, because we're catching every third word.
Oh,
Yes.
That's
so weird. I did test.
It's not a problem with it works with the video, but not with a slide deck.
Yeah.
Voiceover.
So Adia, if you're able to screen share the slides.
Let me see if I can.
I can try and reshare the slides, but it
Yeah, it's a
keeps
visual.
trying to do the voiceover. And then
That's so weird. It worked, but I don't know, like, obviously when I tested it, but I guess it probably, maybe it doesn't like Zoom very much, which I don't blame it. But I don't know. So you're able to turn off the sound?
I just tried. Let's see if this will work. Sorry for the technical glitch here, but the slides are up now.
So I'm not sure where it, you want me to start from the beginning?
I think that's the consensus here. I think it was too choppy. Sorry about that.
Oh, no problem. So I'm now confused because I don't know if I should I try to
you can share your screen. I have the slides up. Whatever's easiest.
I don't know. It's how good are you at just sort of advancing, because I think I would need I need more than one device, which will take me another second. So let's see.
I'm happy to advance. I can try and dance with you as best I can. There's a lot of slide animations, I think is where it was.
There's
also
a lot of slide animation, Mike. That's the problem.
That's where it was having issues, but I will do my best. Why don't we just give it a shot and
You want to try it? Okay.
Sure.
I mean, I don't even know if I'll be, I can also, if you just give me a second, I can pull up the other documents. So I'd at least be able to see the slides, because it helps if I can actually also see them. Not sure. Oh, there it is. All right. We can start from the beginning then, or as close to that as oh. Huh. Okay, my document just disappeared. That was fun. Okay. Okay, so that's not the beginning, but I can,
This is the first slide that I have. Is that not correct?
We could just start there. It's just.
Sorry.
Do it. Yeah, thanks everyone bearing with us.
So I guess I can start there. So in the summer of 2020, a working consensus appeared to be that the racial biases in pulse oximetry weren't exactly clinically significant or clinically meaningful, despite the fact that earlier research seemed to suggest otherwise. And so using the tools of anthropological analysis, my colleague, Amy Moran-Thomas, who's also an SES scholar, helped to bring the biases built into the device to public attention. And if you can advance the slide, and this I think introduced many doctors to overlooked studies in their own medical specialties. Since then, a number of clinical studies have demonstrated how prevalent this bias is and the potential negative clinical outcomes arising from it. And we wanted to, again, offer a critical anthropological perspective because it looks like the primary solution that's being asked, proposed solution to address the biases that we're seeing is essentially the improved quantification of skin color or measurement of skin color. And because the color scales under discussion originated largely in our discipline, we as anthropologists have long wrestled with the problems inherent with them or to them with respect to race. One scale promoted as a possible solution at the FDA hearing, and I think in many of the presentations here, was created at the turn of the 20th century by the Austro-Hungarian anthropologist and physician Felix von Luschen. And he sold chromatic scale kits like the ones pictured on the next slide to quantify the pigment of diverse populations. And of course, these 36 color designations were used in colonial and imperial projects of all kinds, including in his role as a member of the German Society for Eugenics and Racial Hygiene. So the example pictured here is from the Holocaust Museum in Washington, D.C. And we imagine that the FDA and others are unaware of this history when they're highlighting these scales for oximetry testing. So we wanted to call attention to why such histories continue to matter and the questions we need to ask when using any color scale. For today, we'd like to present a more recent case specific to oximetry. And in this case, it's when skin color quantification and measurement was used to investigate oximeter racial bias, it didn't fix the errors. In fact, the opposite happened. Skin color quantification enabled bias and was explicitly used to overlook and dismiss device errors. So using this case, we're going to cover 3 topics that you should be attuned to regardless of what scale you're using. The first are potential problems with applying population level models for skin color and some potential fixes. The role of pathologizing language in producing design error and how to check this language. And the importance of racial self-identification and its continued use. So the 1998 study came out at a time of growing concern about racial bias in oximetry. In this table, which actually is in the next slide, sorry. We can see that patients with darker skin tones were 3 times as likely as those with lighter skin to get a faulty reading. The group classified as dark experienced a 32% device error compared with 11% in the groups classified or intermediate. In comparison to those we find today, the technology appears to have gotten better over the past 25 years. But the ratio of errors found by Schoeding and colleagues in 2020 is nearly the same. The 1998 data should have been a red flag that the device was not working equally well for everyone. But the authors interpreted these disparities in a different way. They concluded that there was no evidence of racial bias in the device, and whatever device errors they saw were attributed to observer bias and thus have no clinical significance. But how did they reach this conclusion? It begins with color quantification. So the researchers in this study used Munsell charts, which are commonly used today in agriculture and archaeology to characterize the color of soil. But at the turn of the 20th century, when those color charts were created, they were widely used to measure human difference in ways that reveal how skin color was differentially valued. In the 1998 case study that we're focusing on here, the 5 yellow-red dirt chart from the US Forestry Service's catalog was held to people's foreheads as a method of measurement. The authors assumed that there should be a dose-response relationship between their color measures and device errors. But when those device errors did not reflect a dose-response relationship, the errors were dismissed as not meaningful. So I think it's probably clear to everyone who's, because we've been through multiple sort of highly specified and fine-tuned assessments of various kinds of color measurements. So in the next slide, I think we have some trouble with the dose response models though, because we're not sure that it's going to be reflected in skin color, right? So they're meant to examine these sort of chemicals or stimuli, but melanin is not a stimulus, and melanin is also not dirt, which is the intended object of comparison for the Munsell color scale. But it's not just about Munsell. These are questions that we need to ask for any scale in use. We also know that from 2 days of talking about this, that skin color is idiosyncratic. So what scale adequately accounts for reflectance and transmittant properties of human tissues, and which will include many things besides melanin? Light readings for skin tissues are individually specific and don't align with dose response models. And in the next slide, we can see too that people with albinism also experience disproportionate pulse oximetry errors because their skin is too light to fall in the range devices have been optimized for. So let's not attempt a so-called race correction for this problem. Pattern device errors that correspond with racial self-identification but appear when a dose response model plus skin color measurement is used likely tells us there's an error inherent to the methods used to study skin color, not that the device errors are meaningless. Second, the authors focused on the challenges of measuring people's skin color as if skin color was the problem to be solved. The device is clearly not working well for people, and that is the problem. So this scale, in this study, they used a scale and found no bias. They suggest that earlier studies that did find bias were wrong because skin color was not quantified as scientifically as it was in their study. And so that's partly how resonant concerns at the time came to be minimized and forgotten. It's crucial that that doesn't happen again. So the overall effect of this preoccupation with skin color is that it locates the problem within certain people instead of with the design choices made while building the technology. How could this be approached otherwise? We'd be interested to hear more about any experiences people have working with multi-wavelength devices and to have a discussion about the colors of light used in devices. The innovations of Massimo's rainbow model comes to mind, for example. And we continue to find the NASA Hewlett-Packard collaboration interesting. We heard dissenting perspectives yesterday, but we've spoken with users who appreciated the many ways they were trying to be thoughtful about their design choices, some of which are listed here. And the MIT engineering professors we met with, together with Michael Schoding's group, didn't know about this HP history at all or about the Massimo rainbow, but they independently thought that it might be the logical next step to add 6 to 8 wavelengths, for example. They also believed that this would have a very low price point to address racial bias issues while making the device globally accessible. And the final takeaway point that we want to highlight here is that people's self-identifications and self-definitions of race matter. We agreed with those physicians who proposed during the FDA hearing that people's own self-identifications or self-definitions must be recorded and considered, regardless of any other measures that come into use. Triangulation helps to understand and interpret patterns discerned in diagnostic and clinical outcomes, which we're actually interested in. And in our case study here, paying attention to self-identification might have caught those errors that were impacting people with darker skin 25 years ago. So to sum up, population-based curves and dose response models for skin color carry heavy baggage from their prominence in maintaining racial hierarchies of the past. If researchers aren't attuned to this history, using such scales without care can unconsciously reproduce the same problematic history in the form of contemporary diagnostic and clinical errors and bias. Individualized light measurements are more likely to produce the best diagnostic and clinical outcome, but any such devices also require transparency and attention. And this is because we're seeing how this might matter, like how it might also go wildly awry. And rather than framing certain bodies or skin colors as the problem to be addressed, scientists should emphasize methods of improving device design. Changing this framing may involve installing checks at various stages of knowledge production. So what proportion of an article is devoted to design errors versus bodily errors. So whether you call something, or is there language pathologizing non-white skin? So referring to healthy people with darker skin color as having comorbidities, or framing melanin levels as a proxy for disease, which, we do see sometimes. And then finally, data using self-identifications was instrumental in bringing attention to this issue and will continue to be crucial as we monitor progress toward eliminating biases in the device or bias in devices. Self-identification should be included alongside other techniques that come into use. And so we'll end here with a recommendation postscript that yesterday's conversation brought to mind for us. Many hospitals are now releasing estimates of the thousands of people they fear have received improper treatment due to this device, and the patient distress its errors evidently concealed. And when we think of this multiplied across healthcare systems around the world over many decades, these are enormous numbers of people who've been unequally harmed and even lost their lives. We believe these human costs need to be not only included, but prioritized in considering the cost of more robust safety testing. Thank you for the invitation to share these notes. We look forward to the discussion together.
Sorry for the technical glitch. Thank you, Dr. Bitson, for being flexible with that.
No problem.
Great. So we'd now like to move into a bit of discussion about everything that we've heard so far this morning. I think a good place to start would be to discuss this objective versus subjective measure, and just more broadly. I think what we've heard this morning is that there are some scales, i.e. the Fitzpatrick scale, the Massey scale, et cetera, that are have proven to not be adequate for various reasons. But I would like to just open up more broadly to hear what people have to say about should we be using any subjective scale. We saw how the Monk scale is more closely approximates what we're trying to accomplish, but I'd like to hear from the group to see if any thoughts.
So I'm confused, which is not hard to do, but it seems like we have overlapping purposes here as we're talking about measuring skin tone, the purposes of device testing, and then we're talking about determining skin tone in the context of the clinical setting, which could and probably would be different. So when we look at visual scales, it seems like those would be applicable to the users in a clinical setting to determine. Regardless of the last, obviously we shouldn't have to determine skin tone in the clinical setting, right? So, but that's a visual version. And when we were talking about actually using a device to measure skin tone, as for device testing and determining whether skin tone even really matters as far as a pulse ox reading. And I'm confused as to what usage a visual would be versus a device type of objective colorimeter or spectrophotometer reading would be used at. Where are we using it? Because we're not going to use the Monk scale for device testing necessarily. My understanding is we use a spectrophotometer or a colorimeter. So
I mean, if I may, so subjective scales like the visual scale, Monk, Fitzpatrick, Von Lucian, subjective, colorimeters, objective, just in terms of terminology, whether that may be but just so we are all talking in the same language. But currently, these subjective scales are used in regulatory, i.e. Fitzpatrick, Massey. And part of the discussion right now is, do we want to say that should no longer be, even though there are many unanswered questions, that is one very specific question. Okay. And I think that's what Dr. Lester is saying is, do we make the decision right now, subjective, which is the current status quo, should no longer be for regulatory purpose. For the purpose of device testing, subjective scales no, there still is a role for subjective scales, or do we say maybe in some cases there are? I think.
Yeah, that's, thank you.
Okay.
I mean, I think Ellis made this point in his talk, which is the ISO standard says you need two people with deeply pigmented or darkly pigmented skin. What does that mean, right? And so I may have gone fast in my talk, but I completely agree with Ellis's point. And what I was proposing was, if the goal is to ensure a diverse population is included in calibration studies, which I think we all agree is a failing of existing studies and maybe one of the contributing factors for why devices do not work equally well across all people, then those types of measures should have some sort of scale beyond just the kind of statement of darkly pigmented. And so using a scale like the Monk scale in inclusion criteria, which are kind of need to be done in a quick way without access to devices in a broad category, and ensuring that it doesn't limit people with dark skin like Fitzpatrick does, and it also includes people with really light skin like also Fitzpatrick does not. I think that makes a lot of sense. And I think from what Ellis showed, I'm biased because I know him, but from what he showed, I think it would make a lot of sense for the standards to shift to say that a scale like the Monk scale should be included as an inclusion criteria for the studies. But I completely agree with you that that is not the same thing as what measurement should be made by the device or at the site of measurement of the device to try to decouple the question of optical properties impacting device performance and racial health disparities impacting health performance or device performance.
Yes.
I also wanted to add that I think it'd be helpful for the standards to share with hospitals. We've seen a lot of articles where hospitals are trying to get real clinical, real world data, but some guidance for them on what scales we're using as device manufacturers, as industry, so that their studies are more comparable to our studies, helping them go through knowing what equipment we use, and should that equipment not be available because some of these colorimeters are quite expensive, what subjective tools they could use which most closely approximate what we're doing in industry. Spelling that out, explaining to them without prescribing how they have to do it, I think would be really helpful to make the body of evidence stronger for all of us as we see real clinical data, real in-hospital data, especially in countries that can afford the equipment we use.
And this is perhaps diving it too deep too soon, but your point about the expense associated with the equipment that we consider the standard now, in collecting data, do we envision that there's a way to develop an objective tool that is based off of the technology we have now that may be too expensive, and a subjective tool like the Monk scale in a way that is cheaper, that we could be sort of more widely disseminatable? This is not my area of expertise at all, and since we have a bunch of engineers in the room, I pose that question.
So the obvious answer to that, at least to me, is a cell phone, right? There's a huge problem with using camera systems to measure color, right? It's just between the sensors and the image signal processor and color adaptation. It's just a whole host of things. However, in your analysis, which is the area I'm currently working in, there have been approved camera colorimeters, and they include a color chart when they do the actual pick the image, so that they have a pseudo-calibrated in situ color measurement that could then be transformed into possibly lab values or an ITA. So it's not as simple as it sounds. There's a lot that goes into it, but I could see a tool like that potentially enabling a lower cost solution than potentially even the colorimeters. Certainly not, spectrophotometers are really expensive, and even the other ones. But that's a tool that everybody carries around with them that could potentially be useful.
And how would bias that's already built into digital cameras play into that? So maybe you're aware of the Shirley Cards and Kodak Gold Film Factory, which is like a historical perspective. Or that's I can talk about it really fast. I'm not an expert. It was Kodak Gold Film that was one of the original color film, and is roughly the technology that digital film is based off of. And the color, what we would consider now modern color balancing, used an image of a fair-skinned white woman named Shirley, who was an employee of the Kodak Gold Factory in Rochester, New York. So a lot of that bias and what we see now, where dark skin is not depicted with enough detail, at least as a dermatologist, when I look at photos that people send to me, I see very stark differences in the detail that I'm able to see of dark skin and light skin. And I'm just curious if you have thoughts on how that level of bias may play into something like a cell phone being a replacement.
I'd like to answer that if I can. You have a photograph, which includes the color scale you're trying to match and the person. And what the software does is it can measure, literally calculate the wavelength of light for each of those things and find out which of those squares on that piece of paper matches the color of the skin closest. So that's completely free of institutional bias or anything like that.
Depends on the color, depends on the illumination though, right?
It shouldn't, because the illumination should affect.
No, but that's what metamerism is. The color, that's what I tried to explain with that metamerism slide. If the pigments of the skin are different from the pigments used to render that color on the print, then you have to deal with metamerism. An even more important difficulty with colorimetry based on RGB cameras is a specular reflectance. We have diffuse reflectance, and that's what we're interested in. That is light that has gone into your skin and comes back and carries the information about the chromophores. Specular reflectance, we can all see it on each other's faces. That's the light specularly, like a specula mirror, reflecting off your skin. And that in dark skin is relatively much higher content than in white skin, because specular reflectance is the same value regardless of your pigmentation. It actually correlates much more with how moist your skin is. If you make your skin moist or greasy, and that is easily solvable with cross-polarized photography. But like you say, it quickly becomes quite messy.
So I wanted to steer back, if we may, to the discussion about the subjective scales, if we could finish that conversation, if there's any additional thoughts.
Just a quick comment. I see in the chat some discussion on Massey and Monk. It sounds like based on what's been presented today, Von Lucian, Fitzpatrick should never be used. Like that. Does anybody disagree with that? Just okay. So that's easy. Done. Now Monk and Matt, because we got to make some progress here, right? Tomorrow there's going to be a standard that's rewritten and it needs to be concrete. I think this is an easier topic than the stuff that I don't understand, which is a lot of what you guys are talking about. So that's why I'm pushing in this space. So, all right. So Fitzpatrick, Von Lucian, we agree no. Monk, we've talked about. Massey, we've talked about. The issue of subjective or not, but I want to comment about what Bill's put in the chat. In the Massey doesn't have a standardized RGB value, which means that if you print it and I print it, we may be using two totally different scales. We have no way to know if they're the same. I think that is a fundamental flaw in the method. Monk has that. And additionally, what Leo's made that Massey has and I can't speak to that with personal expertise, but that it also has other problems. So I would propose that Massey should also not be used based on evidence presented today and those two facts. Does anybody disagree with that and want to debate that?
Can I just respond to that?
Is that okay? I think those are.
Can I just respond to that?
Please, yeah.
And I don't disagree. There's 10 bins or 11 depending. There could be 10 or 11 depending on the Ellis scale as well, because there's the zero or the no pigment. But other than that, they're very similar. And one could say maybe bin number 10 for Massey has some blue tones. But other than that, they're very similar. They almost track. But the benefits of the Monk are that it is quantified. And so I really love that. But I just wanted to say one other factor and then get back to your point, which is skin pigment is one of many static absorbers. It may not be the most important factor. What's really critical is that we make sure that we are inclusive across the entire color spectrum. and across the entire racial spectrum and the ethnic spectrum. We want to be super inclusive. And so it looks to me, as I can just see, without having a spectrophotometric brain, that either the monk or Massey both work. But I'm happy to go with the idea of the monk because it will be more inclusive. And by having more bins and across more spectrum, then we can ensure that we don't eliminate important individuals. It may be bone density, it may be tissue density, it may be other factors that are also important.
Sounds good. Just to clarify one quick thing. I'm not advocating for any scale. I'm just trying to eliminate. I actually personally think that for regulatory, it needs to be objective. We can't use subjective. I think that's another fundamental problem here, and that's sort of what you're speaking to.
Mike, I'm totally agreeing with you. I just wanted to make sure I didn't
Totally
hear
makes
anybody
sense.
talk about other factors. that
Other
might also be
physiologic
a part of
stuff is a big.
that have some sort of correlation with skin tone. I just wanted to make sure we were also cognizant of that.
Sounds good. So does anybody think that subjective scales, whether it's any of it or discussed, should be used for regulatory purposes of device use? Okay, so I'll hand it back to you, but that's curious to see what you'll think.
Can I justify why I think we have to have that open? If you look at neonatal studies and looking for spectrometers in a neonatal incubator might limit ourselves. So I would make it really, if there's a clinical need to allow these scales as a substitute, we should not limit ourselves to not allow it.
Great point.
Yeah, I agree with that. And the use of the scales, the skin color chart, whichever we choose, I prefer monk, should be available for any use where it's not appropriate or accessible to use the objective methods.
Effectively by exception.
I have a question. I'm sitting behind, so. Can I go?
Yes.
Yeah, so just carrying on the discussion on Massey versus Monk, I think I totally agree with Dr. Wilson. We said in terms of comparability, and I also see that when you print it out, there could be differences, which is possible in terms of standardization, maybe some more work needed, but having worked firsthand with Massey scale for a large variety of subjects, seen good correlation with ITA also shown by, I think, a couple of presenters there. I think a couple of things to note here. One is about, we have talked about is like various body size. So if you look at the hand, you see that the shade of the color may change. Like you just look at one side of the hand even there. So when you look at like a picture of a hand versus you look at a spot where you want to match, there is some subjectivity that adds on to that as well. When we use the devices that we're talking about as an objective measure, you also have to account for that you measure at different places and how that is going to add to the variability. So overall, if you have a scale of 1 to 10, and if you want to classify into light and dark, or light, medium, and dark, 2 or 3 levels to that, or you want to use all 10 levels. If you want to use all 10 levels, yes, in a subjective measure, it may be highly variable. But if you want to use a smaller number of levels, but still use a scale that gives you variety of up to 10 and covers the entire spectrum, that could be a slightly different story. So we have to look at how we want to classify these given a scale. So I think from that standpoint, both Monk and Massey could give us that as a subjective measure. I agree that the other two are out of question as well, as everyone agrees here. So those are a couple of points, because if you have the visibility on how you want to take a patient and subjective measure, and that has to be considered because you're not printing it, you're not digitally analyzing it, what is going to affect? So that's the only reason I think Massey is also valuable. And a correlation with ITA, if you look at it, there's 2 categories, brown and dark, that have a large spread. We saw in some of the charts over here. Somewhere in the middle of that is where, like around 4 is where the brown starts and then goes all the way to the dark. So just wanted to bring that up.
So I think we have some questions in Zoom or comments in Zoom. Josh Pfeffer, I think is first, and then we can go to Dr. Monk after.
Hi. I like that last comment. And I think of all the subjective scales, certainly Monk is most appealing due to the standardized correlation with the CIE scale. But you know, as Sandhya mentioned in her talk, there are some features to it that make it seem to me that it wasn't really designed for this purpose. And it makes me just think, what would really be the qualities that we would want in a scale if we were to start from scratch and say, what is the best way to do this? And partly it goes back to the statistical analysis, and that perhaps should drive how we develop a scale if we're going to go that route. And it seems like with a lot of these statistical analyses, we're not using 10 different buckets. There's a comparison of, one bucket versus another. So I'm not sure how that would play out, and certainly the range of pigmentation values varies from site to site. So it seems kind of complicated, and I think ITA can certainly help with that. And to me, possibly a scale that's similar to Monk, but it is more linear with ITA, and really is defined by the known bounds of skin pigmentation across the ITA scale, would be most appropriate. But I think there's also a role for the statistics folks to weigh in here, possibly.
May I speak to that?
Yeah, sure.
Yeah, thank you. So just a few points of clarification. First, on the Massey versus Monk, I do think they map differently in the C-Lab space, as Leo showed, and some of the hands do become rather blue. And in my experience in the social sciences, where people have tried to use the Massey-Martin scale as a way of detecting skin color differences, there are usually notable problems differentiating any of the hands beyond number 7. So that's become one of the barriers to using that scale in the social sciences and for health research. In particular, not only that the hands become blue, which is not really physiologic, but also that they're very hard to distinguish at the higher end of the scale. So I would point out, those two issues as very distinguishing features of the Massey scale versus the Monk scale in terms of its practical use as a subjective scale. In terms of the nonlinearity of the scale, one of the main factors that went into developing my scale was looking at the actual distributions, the maps that we have of skin color around the world. And in terms of being inclusive, that means that there's an actual trade-off between the linearity of the scale with respect to ITA, which there are questions, compelling questions about the usefulness of ITA as a direct surrogate for melanin anyways, and the actual visual representation of human skin tone, which is much more than just L star, but also A and B and other things that are captured, that are not captured by LAB at all, that we're seeing in people's skin tone. So I just want to make it absolutely clear that the scale itself is linear in the sense that it does span the L star range, and it covers that range much more effectively than either the Fitzpatrick or the Massey-Martin. And in terms of a visual scale, I'm not surprised that it's not perfectly linear with respect to ITA, even if it is perfectly linear in terms of the sense that it gets darker and darker and darker as you go across the scale. And to what Vem was saying, one of the decisions in the scale was to really key on L star and to not do too much with redness and brownness, even though we do have some of that represented in the scale because we see that in the world around us. But the main determinant was being linear in terms of L star and to capture that across the full range. And you could bend the scale, as Google has done, as Meta, Facebook has done, in many different ways to ensure that you still are getting some linearity there. You could use 5 buckets, each one with 2. You could do the full 10. There are different ways of bending that scale to introduce the linearity that I think Josh Pfeffer is desiring. So I'll stop there. Thank you very much.
I just wanted to add a point to what Ellis just said, and in response to the kind of question of what is that the scale should include what's known in terms of ITA ranges. I would say I don't think we know what the ITA ranges are. The ITA ranges mostly in the literature come from healthy adults, either in sun-exposed areas or sun-unexposed areas. What is the expected ITA range as you look across the world? As you look at people with albinism, as you look at people with critically ill conditions, as you look at infants, as you look at preterm infants, We don't know. And so to kind of criticize the scale as being going beyond the limits of what we think ITA is, I think that's a fair assessment to kind of compare the scales against each other in the LB plane. I think that makes a lot of sense, but I don't know what those limits are. I think we should keep an open mind to what the limits may be. In terms of, if you do analysis internally and you say, hey, I've looked at a lot of patients and I've used the Massey scale, it seems to correlate with ITA. That could be a reflection of just not seeing enough diversity in the patients that you've seen. I think that's like a core theme that keeps coming back, right? You look around this room, this is not a diverse room. There's all these assumptions we make, and the lessons that people with a DI lens keep telling us is stop assuming that what you see and what you experience is what's out there, right? And Phil put a really important point in the chat. We, expecting a linear range of ITA, does that kind of imply that half the world is light and half the world is dark? No, right? Actually, whiteness is the minority. America itself is going to be a majority non-white country in a few years. And so I just don't know that we should assume that it has to be linear. Having a broad range, I think, is really important. I do think there are some reasonable questions, though, that like Josh brings up a really good point, which is how can we design or adapt the Monk scale to match the goals that we have? One example could be looking at the LB plane, looking at distances between Monk scales, and ensuring that it's easy to tell apart 1 versus 2, 2 versus 3, 3 versus 4. Are they discernible? Are they usable from that perspective? But I think that thinking about limits, what the normal limits are, we have to kind of dispel ourselves from the idea that the current literature represents the limits of human pigmentation. They're much wider, and we need to keep that open mind to that.
To that point, Dr. Monk, I wonder if you could speak on what you see, and others can chime in as well, as the limitations of developing the Monk scale primarily based in the US and in Brazil, and what does that miss in terms of the rest of the world, and how do we grapple with that as we think about the Monk scale aging, so to speak, over the next 2 decades or 3 or whatever the number is?
Absolutely. So yes, I mean, I don't think a single scale, especially one of 10 points, certainly even one of 40 or 150, can fully represent equally all of the diversity of skin tone we see all around the world. I think that's absolutely impossible. I don't think that should be a goal. But the reason why the scale is nonlinear is, as what Leo was alluding to, white people, I mean, I'll speak bluntly, are not the majority of human beings all around the world. And the skin tones that we see, right, on average, and we saw this in the Meta Facebook data that they shared with my scale, there's going to be a lot of people in that more intermediate range, darker skin tone ranges, and that's increasingly going to be the case with demographic shifts in the United States in particular. So I think it's important for us to realize that the linearity of the scale, the non-linearity of scale, put that point aside for a second. What we want to do is capture the most inclusive range of people, and a scale that includes the most people will ensure that people who are very light-skinned, very dark-skinned, and in between will be included in these studies to make sure that these devices work well for everyone. So I just want to highlight that point in particular. I think we want to make sure we cover the full range and be kind of agnostic about the particular distributions that we see, because those distributions are going to change going into the future. We don't know what the distribution will be in the future. And even today, the distribution in the US is different than Brazil, is different than India, is different than Philippines, et cetera, et cetera. So the goal is to be inclusive for these studies. And I think that's what we should look for in a scale.
Yeah, I think there's some flaw to that reasoning. There's nonlinearity and an increase in the number of bins, both at the very light end and at the very dark end of the Monk scale. And so what I'm talking about is a scale that's equal across all melanin content levels, essentially. And I'm much less concerned with the population distribution of people's color than I am of just scientifically assessing the impact of melanin across the range, the full range that might exist. And I think, I'm not sure how many tissue optics people there are there, but it seems like, looking at, melanin in a kind of uniform manner makes more sense, at least in that way. And actually, I'm going to talk a little bit more about kind of our fixation on melanin and its impact on optical devices in my talk. And I think it's actually something that was really missing from the beginning of this whole meeting, a good talk on tissue optics and melanin in the skin. And I think that might have clarified some of these points too.
Great, thank you. Wim, I saw you had your hand raised.
Yeah, I think linearity is the least of the important things because ITA has an arctangent in it. You cannot expect to be the ITA the best linear representation of whatever axis we are talking about, melanin concentration. So I think the Monk scale, the ITA, I thought the linearity was quite good actually. And I also agree with Dr. Wilson that the Massey-Martin is not very different from the Monk scale, except the Monk scale is very, very well quantified. And I think that those are important goals. And linearity differences, I mean, perfection is the enemy of good, I think is the expression. I think we have reached a lot of progress already if we can agree on ITA as a metric and the MST as a color scale on which it might map.
Thank you for sharing. Carolyn, you had your hand raised.
Yeah, I am baffled as to why we care about linearity. And I want to say that I think we need to keep in mind that we want devices that serve everyone and especially the most people in the world. And so I don't think there's any statistical reason to get caught up in if your predictor is linear. Like I mean, I'm not a statistician, but I've have a couple master's degrees and can write some basic code. And that has never been one of the things that has come up as a limitation in an analysis. But I invite anybody with statistical background to comment on that, but I just don't think that that's the focus.
Thank you. I'm not a statistician, but I just wanted to also make sure we're drawing back to that we're working on pulse oximetry. We don't know that melanin is the sole factor here. So we shouldn't create our scale or standard based off of melanin, which is why it gets back to the 50% current requirement standard is not equitable, which for me begs a bigger question is we're doing this melanin work then to make sure that the study representation is equitable. But who's going to be the arbiter of what equality is? What is equitable? I would argue that this group is not qualified to make that decision. So we should maybe, is there a method we can build into the standard that lets a group more qualified be the arbiter of what is quality and have periodic updates to make sure that our requirements meet the diversity of our planet?
Can I chime in just quickly? So first of all, I think if we don't make a decision, there probably is no better group to make a decision. We've got quite a diverse group of experts here between scientists and ethnologists and dermatologists and physicists and regulators. I can't see that we're going to get a better group that's poised to try to figure this nut out. That said, I think there's two objectives which we keep stepping on each other. One objective is to be inclusive, to make sure that all the peoples of the world are included in the kinds of studies. The other objective is to try to figure out where the heck this bias is coming from. We think it's probably or maybe from melanin, and we're working hard to do that studies. But I mean, Paul can show some evidence of studies done on individuals that have different concentrations of melanin on their palmar surface and their forehead, and showing that there's very little bias between those two studies. So there's still a lot of uncertainty as what the root cause of the bias is, but we need to keep in mind what our two big objectives are.
Sure. And Sandy, I'd add a third. We are on a tight timeline. The way to get this kind of information out, both for the testing in real world, meaning clinically ill patients, versus controlled laboratory settings, which are being conducted as well, and getting precise subjective data is to find out where is the problem spot. And it may be, as people have pointed out, multifactorial. Blood pressure, it could be erythema, it could be a lot of issues that are coming to bear. But we may wish to separate and I know this may sound a little harsh, people in this country have not been treated fairly. The bulk of my background has been in high-risk obstetrics, and kids are not treated well when they don't get good maternal care. That's not the issue we're trying to fix. We're trying to decide, is there a corrupter of an instrument that inherently is flawed? It's throwing two wavelengths of light in and making gross assumptions about arterial saturation. That's absolutely blind to race, but it isn't blind to absorbers. It's affected by two things: absorption of stuff, and that includes fat primarily, that's a real corruptor, and scatter. And scatter is water, it's also air. And we've done bad things in telling people that if they don't want to remove their fingernail polish, they can put the pulse oximeter like this. That's not how they were validated. So we need better information, but we've got to go back to the table and say, how can we get this safety communication out there? And I think the best avenue resides right here with at UCSF, with a highly funded system to both collect and objectively compare this information and get it out publicly. I can't think of a better, quicker avenue.
So I appreciate your comments. I think what comes up for me when you're saying that, you know, we have this objective measure and there's nothing else that's the one thing that matters, and it's race blind. Looking around at this room, and we're about to make a decision about how the standards are going to be written. The standards currently say 2 darkly pigmented people. Who wrote those standards? And how will what we decide today look in 20 years from now? So I do think it's actually really important that, I know these decisions are going to be made in a week or whatever, and that is what it is. But I do think it's important to at least get on record. And I would love to invite Dr. Benton and Dr. Moran-Thomas to comment on this. What would be the ideal group to make this sort of decision? I certainly don't feel qualified to say this is what diversity should look like. And I do think that's an incredibly important feature to have in mind as we're making these decisions, even though there are clearly objective measures that we're considering as well. I don't know if Dr. Benton is still on the call.
I'm here. But I don't know if I understood your question. Are you asking about which group has to be diverse? Because I think we've talked about
all of them. And I would love what I would like your what my specific question was is what would you consider to be a good group to make this decision about what diversity looks like in a study population that's going to be validating a device like this?
I think you've already begun to elaborate that with Dr. Monk, right? Which is trying to actually look at something, think about representation. I think one of the troubles you have is you have to actually know what that diversity is. What your I guess sample universe of diversity would be, right? Like you have to look at skin color and not just racial identifications, right? And so that's where your problem is like you actually have you kind of, your sampling universe is a difficult thing to enumerate, be able to then start to think about what the number would be to be able to make the sort of broader case. Perhaps there's somebody who's actually thought about that question. It's because I did talk about this with, I think, Mike, and I have talked about it with Amy. I don't know if Amy has a more succinct answer, because I've been thinking, we were like, well, obviously you have to first start with these racial identifications, but then you have to actually start thinking about the diversity of skin color if you're bound to do that.
Right.
Those things are very different.
Yeah, exactly. I think as you just clarified, the skin tone and race ethnicity are not the same thing, and we kind of have to keep track of both. And someone in the chat mentioned we're trying to pick a scale without sort of knowing the group of people we're going to be applying it to. So there are challenges there, but I also was just interested in your perspective on not only the diversity of the study population we're looking at, but the diversity of the people in the room who make the decision about what diversity of that study population should look like, and the qualifications of such people. That's also. But I'm putting you on the spot. So
well, we did, one of the reasons we offered one of our bullet points was about the checks that we make, the kinds of checks that we make, not only our language, but thinking particularly about, so I've been struck by, and I'm just going to be blunt about it, by the number of times I heard that skin color was like a proxy for something, like a comorbidity, like it's a confound, or melanin is a confounder versus it. And I understand like the technical use, but is it the error? Is, like, so when I'm thinking about what diversity in the kind of recommendation team or the people who are thinking through these questions is, you have to have somebody checking that sort of the way that we're even conceiving of the problem as a problem. And so that means you're not going to only be looking at people who have these sort of fine-tuned technical ideas about light and spectrophotometry or whatever, right? We need people who actually can think with all of the kinds of power relations related to device development. So we cited these anthropologists, Oyarzun and Ballesteros, who actually talk about device thinking and how when you're looking at devices, you're not simply just sort of you're not just simply looking at how it's developed, its history, its the uses to which it's put. You're also having to think about what other kinds of relations it's mediating. And in this case, we're seeing that it's mediating racial bias in clinical diagnostics, right? So that we're seeing a history manifesting itself in a device. You need people who know that that's the case, as you're also thinking about the technical specificities. It's one of the reasons that Amy and I were very keen to participate, because we were like, every time the scale comes up, it's won by the Nazis. Like, like it's not like, it's not an accident, and it's not happenstance. And when you talk about race-blind devices, no, at every point there was a decision made. And those decisions made are reflected in the outcomes that we are seeing. People who can make those checks, I don't know.
Thank you. Thank you for sharing. We have a hand in the room. Yeah, thank you, everybody. It's really interesting.
I just want to highlight, just as co-moderator prerogative, we're running behind on time. Please keep all comments as brief as possible at this point.
Okay, I'll try to. I want to say a lot of this issue was raised by real world research, particularly during the COVID period. And we've all acknowledged that real world research is messy. Caroline talked about that yesterday. A lot of the data are self-reported. You've got an arterial measurement 10 minutes off from an SpO2 measurement. I think that we need to be solving to working backward from the real world and designing things and standards that are going to actually impact that. Because as long as you have messy real world data, and there's a huge thing to unpack. I don't know how hospitals are going to change from self-reported to some quantitative or other type of measure. We're going to have the same types of disagreements when you look at lab data and real world data. So just for consideration, I don't have a solution, but I think that rather than starting with the lab and working forward, it should be real world working back.
Thank you. I see some hands raised on Zoom, so we'll go in order. Josh, you see your hands raised?
Yeah, I wanted to, since people keep bringing up the melanin issue, at least preface what I'm going to mention in my talk with a comment about the extensive literature in optics on the impact of melanin on optical diagnostic devices. There is a lot of information that shows a direct correlation between impacts on optical signals and melanin content. And image quality. Bilirubinometry is what I'm going to talk about, where actually the calculation of melanin is incorporated into how the device works, into its algorithm. So there are other recent papers on photoacoustics that talk about it as well. Cerebral oximetry, and we've done a lot of phantom work on this, most recently on cerebral oximetry, and showing this relationship. So this is this is something that's very well established, and I think even Dr. Bernstein mentioned that pigmentation can attenuate the signal by up to 90%, and there's a differential between the different pulse oximetry wavelengths and the way this happens, and that's due to melanin. So I want to mention one other thing about the going back to the linearity issue, is that if we wanted to test the impact of a variable in kind of our more idealized studies in a computational model or a phantom, we would not vary the parameter non-linearly. We would do it in a very linear manner. And the closest that we can get to that kind of idealized approach, I think we'll be better off in terms of evaluating the bias in these devices.
I'm just going to make one kind of more general comment, which is, I don't know that we have to be specific. I don't know we have to say a scale, for example, by name. It may be that, and for the purpose of the standard, it is right now the bar is on the floor. It is 2 patients that have dark skin. I mean, we don't have enough data right now. We don't have engagement of all the stakeholders. We don't know how to answer the question. We don't even know if we're asking the right question. But we, I think, probably could come to consensus that we can do better than what was done 10 years ago, and do it in a way that acknowledges the limitations in what we know, and sort of set an agenda for what needs to happen to make it better as we move forward. We're not going to come up with the solution today, but we can come up with something that's better than was done 10 years ago and set momentum for doing better in subsequent years. So I just wanted to bring that up. Dr. Lester unfortunately had to step away, so Kelvin and I will continue to co-moderate.
Sure, we have a couple more hands raised and talking to you, Leo. John?
I'm over in the corner. Just assuming for the sake of argument that it is melanin, a requirement of 30% dark skin can still be skewed by the rest of it, and you can still have a substantial difference in performance based on skin and a device that passes, unless you're going to have a requirement that says the effect of skin and melanin and race, whatever it is lower than a certain amount. The diversity of the study pool, the study subject pool alone will not solve.
Thank you. Bill?
I wanted to amplify something that Carolyn said, which I think we should not lose track of. And that, and just don't take this as a criticism of quantifying skin color subjectively or colorimetrically. I am fully in support of that. But as Carolyn alluded to, we cannot lose track of race. That's a terribly important goal that we must all share. If we're going to have equity in healthcare, it needs to recognize race. And the studies that we do need to be racially equitable. And skin pigment is part of that, but it is not the only thing.
Thank you. Leo?
Yeah, I want to echo that exactly. It's something that Adia said in her talk as well, that we can't lose sight of, the self-reported race as a characteristic in our studies. I think something that I think one of the things that I think we're going back and forth in terms of what Josh is saying, and I agree from a scientific perspective, if the question is, we are quantifying a parameter and we are assessing how that parameter directly impacts the signal, then looking for a value that is linear and well reproducible and measurable, that makes a lot of sense. I think the part where some of us may be talking past each other is, if we are going to include a subjective color scale in the standard that will help us ensure that there is an adequate amount of representation of different skin tones in studies, then using a scale that is has been validated by multiple use cases, Facebook, Google, multiple people using it, one where a team member has expertise in building it. It seems like instead of asking, well, should we tweak it to make it different and maybe make it a little bit more linear relative to ITA? That's the part where I think I would kind of take a little bit of discussion with Josh about, where I don't think we need to go there. I think we can use the Monk scale as is, and that will help us achieve some of the goal. But can we use that Monk value as a surrogate for what the ITA is, and then correlate the ITA to some linear scale of melanin, and then use that index to correct the pulse oximetry signal? Probably not. We probably need a different measurement for that. And I think that's also fair to say. So I'll just stop there.
But just to, sorry to jump in, apologies to those who are waiting. Just to add one thing, I want to avoid endorsing any scales. No offense, Alice, I like the scale, but the qualities of the scale. We want a scale that's designed to measure the color of skin in people representative of the world. A statement like that could be enough for the standard, right? Right now it just says dark.
That's right.
So we don't have to go so far as to like pigeonhole us into this area that we just don't know enough about. And so I guess
the only
well, but if you don't, I'm sorry, if you don't pigeonhole yourself, then when we get together to do the standard, we're going to have to pigeonhole ourselves, and the experts are sitting around the table now.
Because people,
but Sandy, if you say
covers that,
nope,
right? That's the problem.
It was not designed to measure the color of skin in a population that's representative of the world, that's standardized and can be reproduced. There's no other scale right now.
Right.
But those are the qualities that keep coming up as we talk about the qualities of the scale. That means that today the Monk scale may be the only one that meets that, but it gives us the flexibility to say we don't know what we don't know. And if a better scale comes about, or a modification to Monk version 3 is the one that we find, it gives us the flexibility. I think it's a mistake to write the standard in a way that is too prescriptive, because we don't know so much.
Well, remember, standards are updated periodically too. So, this isn't set in stone. We do the best we can, and we revisit it when we get more information.
I'm gonna, because I work more in industry than I do on the other side, I'm gonna say what I think all the industry people are experiencing. We're experiencing, as Mike said, no bar, or the bar is on the floor, but the review process has a variable standard based on the individual reviewer that comes up with things that we didn't expect before on a regular basis. And what we want is just give us something that we can predict, that we can do right now, and maybe make it better later if we can't make it perfect now.
Thank you, Mike. William Wilson.
Quickly, I just wanted to agree with you, Mike. I think maybe we could sort of paraphrase. Let's not let what we can't do get in the way with what we can do. We can endorse a scale, maybe the Monk scale, that is much better than what we've had, and then we can iterate from that. But I just want to make one other point about that, which is it's difficult to find individuals in bin number 1 and bin number 10 there. And so the committee may also say that there's a variable numbers in the bins required to represent the global community. And that's, we would need some of our sociologists maybe to give us some of that data.
Thank you. And Wim?
No, I just wanted to make a comment that perhaps it is fair to realize that we are working under a hypothesis that melanin is the cause for the bias. And it might be turning out that we are wrong, and that if we evaluate it 5 years from now, then it might be erased, like you suggested, and not so much melanin. And also, perhaps it's important to know, if you talk about melanin eliminating a lot of light, and that could lead indeed to the bias through SNR problems, not enough light. You can also think of that perhaps white skin is actually causing the bias that is calibrated out by reflecting a lot of light, causing shunt light, and that could also cause a bias. So then it's flipping basically the problem a little bit, if you know what I mean. It's just a different way of looking at it.
We don't know where the devil is yet.
Exactly. And so it's, I think, important to realize that we are now talking about a hypothesis that we're going to evaluate. And if it turns out to be melanin, we may find out quicker with a good PMM. And if it turns out not to be melanin, we also will find out quicker with a good PMM. That's how I think about it. But we should not be surprised if we have to turn the whole standard around in 5 years.
Hold on one sec, sorry. Dr. Hendrickson's up next, then we'll do final comment, and then we're gonna wrap the lunch. Okay.
I want to propose that in addition to identifying a better floor, we also identify a plan to reevaluate the decision-making we're doing today that has a lot of uncertainty. So some kind of timeline and specific plan to look at this again. And although we are diverse in disciplines of training, we are all highly educated people. And I would argue that we are in fact not representative of most people. And just gonna call out, like, our skin color is not representative of most people. So I think we also need to make a recommendation that there is like professional equity advising on these follow-up meetings and also in recruitment of subjects to make sure that the way we reach out to communities gets a representative population in for us to answer these important questions, and does it in a culturally and language appropriate way that really does serve the purpose that we're all here to solve.
Thanks very much. 30 seconds, closures, then we're gonna go for lunch.
Yeah, just wanted to echo back on the comment about diversity and inclusion. Even if melanin is not a factor, I think by including different skin tones, we do include more diversity. So I think that's definitely a positive, going from 6-level scale to a 10, and then defining what the distribution should be, regardless of whether melanin turns out to be a factor. It's a coming change that should be made.
Thanks very much.
It sounds like there are some points that we still need to iron out, but we want to be mindful at the time, and there is food outside, so we want to keep this conversation going, but please do eat.
Yeah. Thanks to Dr. Lester, student Dr. Moore, the speakers from this morning's session. This has been a long one. Thanks for bearing with us. We have lots of time this afternoon for discussion, so this is not kind of the end of this, so keep your thoughts moving, and thanks again. We're going to pause for those who are joining online. We'll see you back at the top of the hour, which is 1 o'clock Pacific Standard Time. Thanks very much.
And you guys solve all this stuff at lunch, will you please, when you're eating food? Thank you.
Roger that. folks.
My cell here.
Hey, everybody, we're just coming back from a short break. For our afternoon sessions. This next session is going to be moderated by Sandy Weiniger. And I just want to mention at the end of today, we're going to have at least an hour and a half, if not more, of discussion. So there will be time to continue the conversation from this morning. As the speakers are talking this afternoon, please keep thinking about the points that you want to make when we go around later this afternoon, so we can make some discrete actionable next steps on several things. So without further ado, I'll hand over to Sandy for the next session on how to account for challenging scenarios and the potential role of phantoms in vitro testing. Sandy, over to you.
Thank you, Mike. Just there's some bandwidth challenges going on. I don't know if it's on my end or your end. So if I disappear, it was not my fault. Our topic this afternoon is an interesting one: how to account for challenging clinical scenarios and potential roles for phantoms in vitro testing. Let me just say a few introductory remarks in general. Number one, we have to try to make progress because, you know, we are kind of the assembled body of experts, and it's better that we try to come to some consensus than every individual company and regulatory body go off and do this on their own. At least that is my approach. I mean, it might be interesting if everybody goes off and does it on their own, or we reconvene in 5 years and then pick the best approach. But I think that would engender a whole lot of confusion, and I don't think we want to do that. So that's number one. Number two is this challenge of what does it mean to be clinically significant? You know, if we have multiple bins that we're accumulating data in, there has to be a reason for collecting data in those bins so that we can figure out how many bins we need. And that's part of this whole discussion about how do we include people and how do we know what the impact of the parameters are. I mean, Wim continues to point out, lots of people point out, is it really melanin that's screwing us up? So we have to address that. Related to what we're about to talk about is this concept of, you know, what are the clinical scenarios that devices are used in? And are we, as, if you will, regulators and standards developers, going to write standards for every clinical scenario that's out there? Remember the picture that I put up that shows you've got an engineering analysis and you've got a clinical analysis, right? The standard that we're working with deals with the engineering performance of the device. How the device is used from a clinical perspective is the practice of medicine. Just as important, but needs to be separated and is handled through different channels. Arguably, we can influence those, but that is not necessarily the subject of today's discussion. What we're going to talk about now is modeling and phantoms to try to tease out performance in avenues and ways that it's really unethical to use humans, because, you know, humans, we don't like to desaturate patients. That's a really bad thing. But to the extent that we can use phantoms, we can assess that performance. So without further ado, I'm gonna, well, we've already introduced everybody, but I think Mike is first up on the tee. Mike can reintroduce himself very quickly, and I'm gonna hand it over to him. Mike is not moving, is he? There we go. Thank you.
I'm Mike Bernstein. I'm the guy who keeps complaining about what the industry wants. So,
well, Mike, let me just interject for just a moment. There is a tension between what clinicians and what we want devices to do and what can actually be built for, you know, reasonable costs and things of that nature. So all perspectives are valuable, and we just have to keep that in mind and weight them accordingly. All right, go ahead, Mike.
okay, so the simulators in general are a very a good way to test the hardware capabilities of the pulse oximeter. I'm talking about the Fluke ProSim here because I was involved in the development, and so I know more about it. But also, because I think it's probably the most popular SpO2 simulator, at least among the people that I know. And one of the challenges is that to make the best use of the device from a technical or a testing point of view is to use a backdoor control interface, which basically is a way that you can make any setting you want on the simulator, not just the ones that Fluke thinks are important enough to put on the screen. So, okay, so what the simulator does is it replaces the finger with an electromechanical device. It's a thing the shape of a finger that you stick into the sensor, and it has photodetectors on one side and LEDs on the other side. So it receives the light coming out of the emitters on the and it puts out what it thinks is an approximation of the finger on the other side. So what you can do, or what it does is it superimposes a wave, the pleth wave, and that illuminates the detector. Okay, so one of the most important things is the detectors measuring the LEDs are broadband, so the device is not sensitive to the precise LED wavelength. Pulse oximeter calibration is critically dependent on the wavelengths of the LEDs. So the simulator can't test the actual accuracy of a pulse oximeter, even if it could simulate a human being, which is something that has been tried by a number of people with spectrometers and a lot of other things. But no matter how much people have tried, we haven't done it. So what can the simulator do? The simulator's parameter that's called transmission in the simulator simulates the combination of finger size and skin color, which is really important. And in the case that we've been talking about a great deal now, it can simulate not the physiological characteristics of the finger, but literally the darkness of it. So between a thicker finger and a darker finger, you turn the transmission way down, and you can see how the pulse oximeter is going to behave at a particular transmission level. And the good thing is, we already know what the transmission levels are in terms of light in and light out for typical the darkest and the thickest fingers we've ever encountered. Because as pulse oximeter designers, we capture that information because we need to design it so we can always measure that finger next time. And the transmission is essentially uncalibrated because we just calibrated it as 100 with a medium-sized light-skinned finger. It was, in this case, mine. The transmission it can be set from 0 to 300. And my transmission number, for example, is about 80. And a transmission setting of 10 is typically comparable to dark skin. So we can see, and again, separate from the other issues of other confounding factors, we can just see if the electronics is sensitive enough to pick up a signal. And since there is no definition right now of what dark skin actually is, as somebody designing pulse oximeters, at least I have a way to challenge the devices so that I can figure out if it's going to work. And the perfusion function, which just like some other things, is really a misnomer. It's called PI on some monitors, a lot of monitors, and it can be set from 0 to 20% of the total amount of DC light coming through the finger. Now, in a hypoxia test, while people are trying to do it, it's very difficult to control the perfusion and very uncomfortable for the subjects. So with the simulator, the full range of normal and I would say also abnormal perfusions can be covered with 0 to 20%. A lot of people think that they can pick up accurate sats at perfusion levels of 0.02. In creating that kind of a situation with a real human is not necessarily, and I don't know if it would be tolerated or if it would even be possible to do it in a stable manner. But the simulator allows us to go down there. And again, okay, there may be other factors with a real human over the simulator, but if you can't pick it up on the simulator, you definitely won't pick it up on the human. So it's a good place to start before you start torturing people trying to do the test. Another thing is that testing heart rate claims on a pulse oximeter, heart rate accuracy claims, is also really hard to do on people because the heart rates don't change very much in DSAT tests. And if they go particularly high, they discontinue. So generally simulators are used and so far have been accepted in regulatory submissions. But what I like to say over and over again, simulators can't be used to measure accuracy. So what my favorite thing to do with the simulator is, and it's something that we're trying to do for Open Oximetry for all of the pulse oximeters, is run a series of tests trying to find the edge of performance. And by the edge of performance, I mean if you start out at a very low light transmission level and you go down in light transmission until the pulse ox doesn't work anymore, and then go back up one. If you turn the perfusion, if you cut the perfusion in half, I would also expect it to not work. In other words, that as I was saying yesterday, that cutting the perfusion in half and cutting the light level in half are the same thing to the circuitry in the oximeter. They certainly aren't the same thing in the real world. So you get this curve of where you've increased transmission and decreased perfusion, and you get this line that represents the noise floor of the instrument. Well, of course, sometimes that doesn't come out to a straight line. And sometimes in the process of this, when you push something past the limit, you discover rather than not giving a number, it gives you some extremely wrong number, or the value starts drifting around, or other unexpected things happen. That, leads you to believe, well, this pulse oximeter probably isn't ready to be marketed. Of course, with a lot of these ones, they're already in the market being sold as health and wellness devices. So you can test the two things that I think are most important in pulse oximeter design. It's how dark of a person will it work in, how low of a perfusion will it work in, and is it well enough designed that it cuts off at the point where it stops giving valid readings, or does it keep reporting long after it's past its measurement limitations? See, did I put the chart in there? Yes. So this data gets shown graphically, and this is way back when I was at Nelcor. Somebody named Tom Yorkey first used this graph, and he called it the COP chart. to police consistent oximetry performance. And we didn't think it was that funny either. But I think the thing to take away here is you get this thing that where you can see, well, there's dark skin and low perfusion, dark skin and high perfusion, et cetera, and so forth. And the low floor there is the N395. And I think the current Masimo RAD7 is very similar. It'd be hard to tell the difference, I think, because all the really good ones get to about there. And the other one is the ChipOx, one that I was developing at the time. And we went and did that test, and we found, oh, look at that. It has a problem as the light gets brighter. It shouldn't do that. And we knew the shape of the curve should have been more like the Nellcore. We would have had to spend a lot more money and a lot more time on it to get closer to the Nellcore, in noise floor. But we were able to fix that once we realized we had a problem. And this kind of testing allows us to the manufacturers to fine tune their devices before we go and take them into a lab like Dr. Bickler's and embarrass ourselves with something that doesn't work, and also waste his time and waste our money. And it also allows us, when we're doing the same thing with Open Oximetry, to get an idea of the range of performance of the device. We could predict that one $20 pulse oximeter, for example, wouldn't work at all on people with dark skin, or it wouldn't work at all in low perfusion, and recommend to people not to buy it. So the only thing that I'm going to say is, in conclusion, you can't use simulators for accuracy testing.
Okay, thank you, Mike. So let me first, being the moderator, let me pelt you with a few questions.
Sure.
So I want to distinguish, if you will, between the noise floor of the simulator and the noise floor of the device. So the front end has to measure the amount of light that comes out of the pulse oximeter. Right. So for darkly pigmented individuals, there's a whole lot of light coming out. That's not particularly hard to do unless it saturates the front end. But for translucent little babies, where you have a minimal amount of light coming out, that might drop into the noise floor. So I'm trying to get a handle on the noise floor of your device. And the opposite is true, I think, for the output, right? For the output, for a deeply pigmented individual, there's very little light coming out from your LEDs to beam back into the oximeter.
Yeah, that's right.
So I'm just trying to make sure that doesn't fall into the noise floor when we start to deal with, perfusion index and things like that, percent modulation.
Without getting into the details, I was, when we started designing this thing, I was frustrated with the other simulators that we had that tried to use 12-bit ADCs because they didn't have enough range. And I insisted on using 16-bit ADCs and having them be one for light and one for modulation. So the first problem, which you didn't even ask about, but I was going to mention, is the problem that the waveforms don't even look like waves at low perfusion. Yeah. Was fixed. The second one is, at the time we made it, the noise floor of the simulator was down by a factor of about 10 for many of the oximeters that I was familiar with at the time. And the newer generation of pulse oximeters with these integrated chips that are made for smartphones and such are significantly lower noise. And it is challenging to test those on it, but you can, if it's sort of ironic, has good filtering as well, you can still do useful testing on it. But the truth is that it's getting outdated.
So now for the $64 question. We have acceded to disclosure requirements in our standard because nobody could agree upon anything. And of course, that makes for very weak test methods, if you will, because there's no acceptance criteria. Do you envision that we could say here is the minimum percent modulation that one should detect?
Yes, I absolutely think that should be part of a validation test. And if we get to the point where the noise levels on the current simulator are a problem, we can build a new one.
So we would have to then, I'm presuming, define what our DC levels are that those tests occur at.
Yeah, well, you would, if you had a low perfusion limitation, you'd have to test it if you wanted to test it separate from the DC at a high DC level. And of course, at a high DC level, you're out of the noise floor. You're way up above the noise floor of the instrument.
Right. Right.
And and then the same goes for if you wanted to test low light at high perfusion, you can also do that out of the noise floor. You just can't.
Yeah, sorry, go ahead, please.
You just can't find the noise floor. You can't find where and that would only be of a very, very good device. What would happen would be the low perfusion and the high and the low light characteristics of the oximeter under test would look better than anything that's on the market today, but would be the levels of the simulator, not the levels of the device under test.
Okay, and final chairman's prerogative question. Let's talk about pigmentation, because currently, as I understand it, at least from the front panel, when you dial in dark, it attenuates both channels, but you can attenuate each channel individually in your manual mode?
Absolutely.
Okay.
And again, that would have to be specified as a part of the test method. The test method would be pretty easy to write up.
Okay, any other questions?
I wonder,
We got Leo here, Sandy.
Go ahead, Leo. And I
One thing you
Rolf
talked
next, I guess.
One thing you talked about there is, the ability to attenuate the signal, and that kind of would be mimicking the mu A, the absorption coefficient difference.
Correct.
But there's also scatter coefficient differences. Is there any way to account for differences in scatter in these test methods?
I don't think so.
Yeah.
Right.
So we good point.
It's a
We
fake
have
thing.
different sensors for a reason.
Yeah.
The simulator.
I mean, I don't want to steal Chethan's thunder because I think, but his work has been really important in showing that the effect of scatter may be quite important in explaining the underlying cause. And there are ways you can mimic scatter, right? Adding a scattering layer of some sort. I don't know if you want to design just thinking out loud, design a way that has a fluid-filled channel that you can fill with some sort of fluid that you control.
Well, I think Josh is going to talk a little bit about that in his talk. So why don't we hold that topic as well? Rolf, did you have a comment, or you're good?
Just a question, basically, to have it practical. If you consider to disclose some requirements in the standard, is the manufacturer of such a device willing to specify the performance in this range, and how would then such a device to be calibrated and instrument controls to be a viable device for standard compliance? And is it only one manufacturer, or have you then singled out basically
compliance to standard with a one single manufacturer of a test device. So similar to what do we expect from co-oximeters? If it becomes a formal test device, we have to also be sure that we can buy those devices with the specified performance for the next year.
Right, and what happens if Fluke decides they don't want to be in this business?
Yeah, the problem was actually the thing was not in production for 6 months due to chip shortages, but it's the same problem. And the answer is I don't know if anybody else will. And I think that Fluke can be convinced to do it. But, you know, like everybody else, they're busy and there has to be an incentive. And I think the incentive is if their device is the only one to meet the requirements of an upcoming standard, I think they would do it.
Julian and Phil?
Yep.
Then Phil?
Yeah, thanks. Yep, can you hear me?
Yes.
Right, so I wonder if Mike could comment on any interaction between the motion simulation performance of the simulators and any of the topics we've been discussing here in this workshop, or can that be handled entirely separately?
The motion simulation and the ambient light simulation and all that stuff are all just they're motion artifact that was recorded in a test study, but they're all superimposed on the PPG. So it isn't really a motion test, which tests the motion of the sensor on the finger and stuff like that. So it's not something that I think should be taken that seriously.
And in fact, we have a small subgroup which is evaluating that concept, and we're waiting for them to make those same conclusions. Phil?
Mike, is there any rule? Turn that off. Mike, is there any way to use the device to assess performance of reflectance oximetry, or is that just not part of the configuration?
Well, that's an ongoing, to be absolutely honest, I've been pushing Fluke to do the reflectance version, and they know they have to, but it's just one of those things. So I have a colleague of mine and I made a reflectance adapter for that simulator. It works really well, but we haven't formally validated like they have with that. And so it's good for development purposes. It is basically it's a PC board that has a sensor and a LED on it, and then a series of 3D printed adapters that allow you to connect it to your watch or your ring or chest patch or whatever particular device you're doing. And so far, a company's named Springer Design has done about 8 or 9 of them. So there aren't a lot out there, but most of the big major companies doing reflectance stuff for mobile biometrics have them now.
Any other hands? Valencia, is your hand up? I can't quite tell. Please.
Yes, great, thank you. Mike, if you could comment on the performance of the ProSim versus something like the WellTech oximeter testing device.
Okay, well, that's a good question, and I'm going to dive in and get a little technical here. But the the Fluke simulator receives the light in an analog detector, and the connection from that to the LED that shines onto the device under test photo detector, it's a complete analog channel with multiplying DACs modifying the amplitude of it, but not filtering that channel at all. As it is whatever's on it. The WellTech has a digital front end that detects when the LED goes on and then creates a pulse on the output with what it thinks the pulse duration was on the input. and does not contain any of the electrical noise or other artifacts that are there on the LED. So there can be, the whale tech is good in that it tests a lot of things, and you can test low light and low perfusion kind of on it. It's a little more limited on the ranges it can test, and its resolution is lower, so you can't go down to as low of a perfusion before the wave turns into it. But before I sound too negative, they've got them in stock, and it's a lot less expensive, and you can do a lot with it. But I don't use mine, I use my Fluke.
And they have a reflectance adapter.
And they have a reflectance built in. But you still have to make some sort of 3D printed adapter to work on their reflectance thing. But it, as I said, it's quite useful if, you know, you're just starting out a project.
Okay, in the interest of time, if there are more questions, let's hold them or put them in the chat. I think our next presenter is Dr. Patel.
Hi. Fiddling with my buttons here. But I think I'm all set. This has been a really interesting day listening to all the different perspectives. So I appreciate the forum. There's been a number of things that have that made me wanted to comment, but I kind of reserved a majority of my comments for just including in what I'm going to share. So if what I talk about doesn't exactly follow what you see on the slides, it's really just kind of me editorializing as we go. Do you see which screen are you all seeing?
We see your
not the right one.
Yeah, wrong one.
Let me switch this.
Maybe click that display setting. Yeah, that.
Yep. There we go. Okay. Wonderful. So so thanks for the invitation. I have been working on low-cost point-of-care devices for low-cost point-of-care optical devices for making clinical measurements for some time. A lot of this work took me in the direction of trying to create low specification versions of transcutaneous optical sensors, bilirubinometers, like what Dr. Pfeffer was talking about, and then that line of work particularly took me into looking at creating low specification bilirubinometers in areas where the burden of neonatal jaundice was the highest, and these were in sub-Saharan Africa, where the issue of pigmentation and its effect on bilirubinometer accuracy got me thinking about how transcutaneous devices make quantitative measurements, and ultimately, from a theoretical perspective, how computational simulations of light tissue interaction could help inform our understanding of where things go awry, from the intent of the design of the devices and the principles involved in the design of the devices, and then what's actually reported in these clinical studies. So this work is really the work of grad student in my lab, Shahryar Arifin, and has been able to be performed thanks to collaboration and support from GH Labs, and I'll talk about what all we were doing there. But I started making changes on what I was going to talk about, just to try to fill in the gaps on some of the things that that had come up. But I want to start off by saying that the original pulse oximeter theory is based on a simplified approximation that works, and it works really well. It's worked well enough to change the face of modern medicine, thanks to the use of oximetry and preoperative or postoperative care and surgery and all these things, right? But it's really just saying that that the light going through a tissue, right, in this case like a finger clip, at red and infrared wavelengths, holds information related to the oxygenation of the blood, and you all know that, and that's been talked about quite a bit. But what I want to lean into here more specifically is that the governing equations and principles that serve as the numerical or the analytical basis for quantifying oximetry or oximeter levels from optical signals is rooted in the Beer-Lambert law for light absorbance. And this is an approximation. This is an approximation in physics that thinks about how light would be attenuated by matter if the matter was only absorbing and these absorbers had certain criteria. And based on this physics, right, taking into account absorption, not taking into account scattering, a set of governing equations were developed and ultimately solved for to come up with this whole idea of the oximetry ratio R, which is this ratio of ratios, this normalized approach that tells us something about the ratio of oxygenated deoxygenated hemoglobin. And this isn't a deterministic solution. What's known is that you can take these oximeter measurements and you can calibrate them against oxygen saturation measurements from SaO2, but it won't exactly match up. And there's a number of reasons why that doesn't exactly match up. But part of what what's going on is there's this some fundamental basis, and part of it is some instrumentation factors, let's say, but ultimately empirical calibration is always necessary. And so doing these calibration studies is an important part of ultimately constructing a model for our oximeters. And what's been hinted at in a lot of the talks today is that it's been known that oximeters carry some degree of pigmentation bias, and this comes from some smaller scale human subject studies, but also theoretical studies that take into account this kind of stuff, the theory of light's transit in tissue, and one really good way of simulating light's transit in tissue is to use Monte Carlo simulations, and these are great because, unlike analytical equations that are based on physics, the Beer-Lambert physics, they can more comprehensively take into account all the optical interactions that are happening, as well as the order in which those optical interactions are happening, the layer dependence of how the light interacts with, let's say, a certain type of absorbers and scatterers first in the most superficial layer, the epidermis where pigmentation lies, versus as the photons transit through the tissue. And it's really a brute force and not really that clever of an approach. It just bombards a model that's been constructed of what tissue looks like with billions, millions and billions of photons. And then it just records what comes out. And so its simplicity in large part gives, provides for its strength. In addition, using Monte Carlo modeling of light transport in tissues to evaluate, biomedical optic devices is something that's been going on for a long time. And to that vein, much work has been done in the characterization of tissue optical properties, understanding how to construct these models and how the models inputs and outputs can inform things. And really more importantly, right, a bunch of work has been done that shows that the ratiometric, well, first off, just we've heard from a number of people of how optical measurements are affected by pigmentation, right? That much is evident just by what we see with color. Right, but in addition, this ratiometric factor R that's used to quantify oximetry, right? Monte Carlo simulations have shown that as pigmentation changes, the volume fraction of melanin in melanocytes in the epidermis changes. This ratio, the intensity of the signal changes, right? That's kind of fairly intuitive. But then the other thing that changes is the ratiometric factor, the oximetry ratio, or the AC/DC level of the oximetry signal, also as a function of pigmentation. So this, this theoretical idea that pigmentation affects oximetry signals is not only not not new and has been around for a while, but is also really well supported by these computational simulations that inform what we observe in real life. Now, to start to look at how simulations can be used to affect quantification accuracy, right? Getting to this question kind of along the lines of what we were talking about before, about how these simulators and models can look at accuracy. It's important to just revisit and understand how we get to quantification of measurements in oximetry. And the way we get to quantification is by performing this calibration study on our oximetry ratios R that we measure from a given device across a population cohort that goes through this desaturation study. And then from those measures, we generate a calibration model, and then that calibration model is then used to then inform our measurements of oxygenation, right? And so if you're kind of paying attention here, then if the oximetry ratio R changes as a function of pigmentation, if the signal intensity changes as a function of pigmentation, the oximetry ratio R changes as a function of pigmentation, then it should also make sense that these calibration models are directly informed by the makeup of the calibration cohort that constructs them. And so what we did is we looked to extend Monte Carlo simulations of light transit in tissue into this new paradigm that Shahriyar has convinced me to call in silico simulations of oximetry. And I really like that description because it it shifts the focus from just looking at how light transits through tissue to performing simulations of clinical scenarios or measurement scenarios that help inform what's going on in the world around us. And so what we did was, instead of performing single simulations of light transiting through tissue, we through a tissue or through a few different sets of tissues, we created hundreds and hundreds of finger models that were all informed stochastically with optical properties, meaning the optical properties were selected from statistical distributions that were informed from the literature based on the physiological expected values of different chromophores or the anatomical structures there in the finger. And so we have distributions from which each finger model samples an optical property of scattering in the epidermis, blood volume fraction, absorbance, big bilirubin, and we do this just computer simulated calibration study. We did these much more comprehensively than what the ISO or the FDA 510K, let's say, necessarily requests. We had 200 individual fingers. So that kind of represents 200 individual sample participants. They went through this deoxygenation protocol. We simulated what the oximetry ratios are where. And from those simulated oximetry ratios, we created a calibration equation. And then we did that 5 different times for 5 different pigmentation distributions of cohorts in the enrollment of enrollment cohorts. And then using those different calibration models, we tested what the quantification of oxygenation of SpO2 would be on different cohorts of finger models, again, stochastically or statistically informed, but this time with, let's say, different pigmentation population distributions. So what does that kind of mean? So here's just a plot where we're looking at the fractional volume of melanosomes on the x-axis versus the number of fingers or participants in our computer model, and we've created kind of this paradigm for looking to mimic the Schoeding paper where they had white and black enrollees. We used low melanin and high melanin cohorts, and we created these distributions for a low melanin cohort where we had a distribution of pigmentations, meaning, ultimately all these people in the low melanin cohort are not the same pigmentation or not the same color. Their distribution generally that's lower than the high pigmentation cohort, but they're not really disparate. There's overlap, and ultimately we're seeking to reflect the continuity of pigmentation that exists amongst people. And so then we created these calibration distributions based on different mixtures of enrollees, either following the inclusion guidelines where we have 20% of the participants darkly pigmented, all of them darkly pigmented, all of them lightly pigmented, or different mixtures, 50-50 or 80-20 the other way with dark and high pigmentation. And then we created different test cohorts, either all low melanin, all high melanin, or a test cohort that followed the same 80-20 distributions. And these, these histograms are really just what the output of our stochastic sampling created in these studies. Now, the first thing that we did is we looked at what the oximeter ratio R is a function of the fractional volume of melanosomes. And just to take a quick diversion before I kind of go on with what I'm talking about, we did this, skewed version of the simulation where we assigned the scattering to 0 through the sample. And when the scattering was assigned to 0 across all the layers in the sample, the interesting thing that was observed is that actually you have the exact same oximetry ratios R regardless of your volume fraction of melanosome, pretty much saying that, hey, the initial analytical framework for calculating for not only calculating oxygenation, but also for attempting to correct for the static effects associated with chromophore, or with the effects of static chromophores in the tissue, like pigmentation and everything else, that works really well according to that construction if there's no scattering, right? But the reality is that there is scattering, and the ratiometric measure R is not exactly straight when it comes to pigmentation. There's this nonlinearity, and this nonlinearity ultimately results in these differences in R that are associated with pigmentation. Nevertheless, we can create, using this 80-20 mix that the ISO stipulates, we can create a calibration equation, and this calibration equation can meet the guidelines that they're typically required of these studies. Now, the thing that we saw is from our computational simulations, it was not surprising that we got different calibration equations for different pigmentation distributions of our enrollment cohorts. Now, using these different cohorts helps us understand how the quantification error looks in oximeters. And so if we use the standard calibration distribution and we look at the differences between all low melanin versus all high melanin cohorts, we see the exact same trends and results and very similar magnitudes on our first order approximation to bias in darkly pigmented individuals versus lightly pigmented individuals, as was observed in the Schoeding paper. We see overestimation in darkly pigmented people, and we see the scale and magnitude of that overestimation increasing as oxygen saturation decreases. This really directly informs how oximetry quantification would look, all right, if we could hold all the variables that can confound human subjects measurements and make them messy and difficult, if we can hold them all the same, right? And so I think it's revealing that one, there's a wealth of evidence just from understanding light tissue interaction that show, studies also show that pigmentation impacts the oximetry ratio R and clinical measures of oxygenation in lightly versus darkly pigmented people. In addition, from first principles, we see the same results in computational simulations where we hold all these parameters constant. So, you know, I get it, right? Like we're all looking for this, you know, human subjects clinical validation for where the basis of a bias in oxygenation and pigmentation is coming from. But we're having all of these arrows pointing in the same direction that pigmentation is a primary factor. So to say that, you know, we don't have any idea where this bias is coming from, or it might be pigmentation, I think is a little, you know, disingenuous. Absolutely. And I'm going to talk here real quick about other things that can affect the signal, but ultimately pigmentation is really driving things in intuitive and scale appropriate fashions as it relates to measurement bias. Now we did.
Sorry for interrupting. You heard my mental 2-minute warning. So thank you.
Okay. Yeah. So we looked at different test cohorts, and I think this is just, you know, examples for me to make a bigger point that computational models and in silico models can help us look at other more complicated factors related to biophysical changes, pathology, these kinds of things, right? And so the test cohort where oxygenation distribution was taken from a paper that reported the oxygen saturations of patients admitted to the intensive care unit. We saw that our simulations, when the native oxygen saturation populations look like the ICU cohort, similarly would show this overestimation bias. Our model, you know, reflects the Schoening paper in this overestimation. It also shows that this overestimation can result in the misattribution of normoxic conditions to patients that are hypoxic and darkly pigmented. And so we can use these simulations to even start to look at diagnostic performance based on how we're constructing our calibration cohort. So this, I think, is something useful to think about in terms of how models can inform the ISO, right? And that there's a lot of talk related to how we equitably you know, inform the study of pigmentation and oxygenation and enroll in the validation and calibration studies. These simulations kind of suggest that there's quantitative ways in looking at those factors. So you know, these simulations are reflecting what's being observed in the real world. They're you know, there's still things that we would need to do, right? Much of the talk has been on how we're going to quantify pigmentation in an effort to better construct studies that evaluate equity and bias in oximetry. But the way that our models are informing them is based on work that really arises from, you know, path, you know, and not in vivo measures of pigmentation. So how do our measures of pigmentation align with these measures of pigmentation that we're looking for? We also looked at other factors, and this just maybe is one last thing that I want to say to you know, to let's say enrich the conversation. Now, these ideas that you know, pigmentation is affecting oximeter quantification accuracy, but other things are doing that too, are absolutely not taken lightly by me at all. And in fact, we've looked at how other factors that can contribute to oximeter quantification accuracy look in our models, and we see interesting things, and warrants looking at these more closely. So met hemoglobin and dyshemoglobin rates in populations are something that's worth looking at, particularly, in the context of other explanations for bias in African Americans that are reported in the Stoning paper. Methemoglobin levels are associated with G6PD deficiency, which is prevalent in sub-Saharan Africa and places with high rates of malaria. And so this notion that, changes in optical properties of people or population differences in GP6 rates can contribute to the bias that we've observed is worth taking with gravity, right? What we saw in our simulations is interesting. I'm going to kind of skip these details, right? But I'm going to focus, let's say, on this figure here. But what we saw is that increasing methemoglobin rates actually changed the bias in the opposite direction as pigmentation. So if you're darkly pigmented, you're going to have overestimated SpO2, but with higher rates of methemoglobin, the model suggests that is going to counteract pigmentation and shift the bias in the other direction. This bias is not just standard, but it's changes as a function of oxygenation level. So it's complicated, right? But pigmentation still at a primary level is what's driving this. The other thing that's come up in these conversations is noise and how noise contributes to accuracy. And just a quick thing that I'll say is our simulations are telling us that that increases in noise, which we can readily implement into the model, this is shot noise, right? Show that while we don't really do anything to the bias, we do increase the variability. And in fact, actually, as SNR gets higher, we start to have stronger biases, or the measurements more sharply aligned with theoretically where they should be. Whereas as signal noise decreases, the bias trend is actually to become closer to the green line, despite the fact that the precision of the measurement is changing dramatically. So anyway, these are all just examples of what you can do with computational models in the study of oximetry. I focus a lot on how the models are not comprehensive, and these slides are how I was planning on concluding. Right, there's much that we already know about optical properties in the skin, but understanding distributions, variations, changes associated with pathology, biophysical changes that are associated with function, and model construction. These aren't things that are all, perfectly elucidated. And so we still have some way to go in better informing the model so that we can expand it to include these interesting scenarios that we're talking about. But bottom line take-home message is that these models, from what we're seeing, very strongly support the notion that the primary cause of bias can be directly attributed to pigmentation in these computer simulations. So I'll leave it there. Sorry for going over by a few minutes.
All right, thank you. Questions? We have time for one or two quick questions, and then we'll follow up later with more questions and discussion. We're only an hour behind, I think, right?
A lot to say. Everybody has a lot to say, I guess.
That's okay. I mean, it's very important to air these out. Yes, please go ahead, Rogerio. Please keep it brief.
Hello, and thank you for your presentation. I love it. And I believe that this work is it's very similar to my work. And I have a pulse oximetry and a technology that don't use the table, I use the mathematical model. And I'd like to know if you I understood that your work is divided in two parts, and a pulse oximetry and a simulator. And I'd like to ask you about regarding the if you tested validated this mathematical model that you did in pulse oximetry using humans, and if you validate this simulation, this simulator using something like the saturation study or something like this.
Yeah, those are all good questions. So we absolutely have not been able to validate these models against human subjects. Doing that would be tricky because we would have to be able to quantify the compositional makeup of every chromophore in the finger with certainty, right? So we kind of need the finger to measure afterwards, and we haven't done those studies anyway. But that's I think an important part of the future direction that we need to go in linking optical properties and the breadth of optical property measurements with across population distributions with the more sparse sets of optical properties that have been measured from tissue specimens. The second thing that's challenging about validating these measurements is that oximeters aren't providing direct, or at least commercial oximeters aren't really providing direct outputs on the red and infrared channels. And so, work that's been done by both our collaborators at GH Lab and other people out there, have led to getting these types of devices, but we haven't done these direct validations on the experiments against human subjects matters. Now, validating them against phantoms is much more reasonable, and that's, I think, where the next steps are going to go. But validating a phantom against a phantom, or validating a computer simulation against a in vitro simulation is, I don't know, it's useful for something, right?
In the interest of time, we're gonna be very brief. Phil, brief, please, and then Ravi, briefly, please.
Oh, I just wanted to point out the obvious that your results recapitulate almost exactly what we reported in 2005 and 2007 with respect to the influence of skin pigment on pulse oximeter errors at low saturation. And the same for the methemoglobin results. I mean, they're identical. Your models capture the reality in humans very, very well. So congratulations.
All right, Ravi,
thanks,
quickly, please.
Hi, Chetan. It's a nice talk. I have a question. What happens if you translate the same method, what you've done for a transmissive model, to a reflective mode? Do you see any kind of limitations on that?
Yeah, we see
the
differences.
calibration equations and other things.
Yeah, there are differences. There are absolutely differences. Just related to the, the differences primarily arise from the optical.
Do you see any kind of a significant difference in the calibration equation, what you derive for the pulse oximeter? And then if that is the case, then which one do you suggest is a better method to use? Go for a reflective method or a transmissive mode then?
Yeah, I don't know, the nature of quantification bias is multifactorial, right? Or in particular, it's related to the misalignment of the reality of the physics with the first order approximation of the physics model that informs the construction of the measurement. But the second part of it is really has to do with how we enroll the calibration study. So I think that's another thing that I would direct the ISO towards is, carefully specifying how the calibration studies and validation studies are enrolled. Obviously, that's kind of what they're looking at doing by having the pigmentation criteria, but it's possible to be even more specific than that. As far as reflective,
I look forward to your specifics on paper so I can understand what you're talking about. Anyway, all right. I'm gonna thank you, and we're gonna move on, as I said, because we're good and late. Josh is gonna talk more about pigmentation and measurement systems.